Hello, and welcome to The Sleepy Scientist. This is the place to slow down, unwind, and let gentle stories of science carry you toward rest. Tonight, we'll be drifting back into the age of dinosaurs, giants who ruled the Earth for more than 160 million years. Before we begin, I'd love to know, where are you watching from tonight? If you're new here, please consider giving the video a like and subscribing. And to those already subscribed, thank you so much for being here. Don't forget to click the notification bell so you won't miss the next upload. Now, a little reassurance. This video is made to help you relax. I hope it isn't so interesting that it keeps you awake, but if it does, at least you'll be a little wiser when you finally drift off. So settle in, let your breathing slow, and picture the ancient world stirring to life. What was it really like to live in the shadow of dinosaurs? 252 million years ago, the world had just endured the greatest catastrophe life had ever known. The Permian extinction, sometimes called the Great Dying, had swept away nearly everything. More than 9 out of every 10 marine species disappeared, and on land, forests withered and animals collapsed in number. What followed was a long, fragile recovery, and into that vacuum of loss stepped the earliest ancestors of the dinosaurs. The Earth of the Triassic was a world in transition. All of the continents were fused into a single giant landmass known as Pangaea, stretching from pole to pole like a cracked, sun-baked puzzle. Much of its interior lay far from the sea, making the climate harsh, scorching in the day, cold at night, and often bone dry. Seasons could swing from blistering drought to sudden bursts of rain, shaping landscapes of red deserts, flood plains, and river valleys. It was not yet a lush kingdom of giants, but rather a testing ground of survival, a place where new forms of life experimented with what worked and what did not. Among the survivors were archosaurs, a group of reptiles destined to branch into 2 great lineages, one leading to crocodiles and their relatives, the other to dinosaurs and eventually birds. At first glance, the early dinosaurs were not the towering titans often imagined. They were small, light-footed and quick, darting through undergrowth and over open ground like shadows under the relentless Triassic sun. One of the earliest known, Eoraptor, was scarcely bigger than a dog, with long legs and sharp teeth suited for catching small prey. Another, Herrerasaurus, was more imposing, yet still modest compared to its descendants, standing perhaps a few meters in length and moving with a nimble gait. These early dinosaurs were not alone in their world. They shared it with a host of competitors, especially the Pseudosuchians, the ancestors and cousins of crocodiles. Pseudosuchians came in many shapes and sizes. Some resembled armoured tanks, others were swift, 2-legged predators. For much of the Triassic, these crocodile relatives seemed to have the upper hand, dominating ecosystems and keeping the dinosaurs in a supporting role. It was not yet clear who would inherit the Earth's open spaces. What set dinosaurs apart, however, was their stride. Unlike most reptiles, whose legs sprawled to the sides, dinosaurs evolved an upright stance, with limbs tucked directly beneath their bodies. This new architecture allowed for more efficient movement, better support for body weight, and the possibility of growth beyond what most reptiles could achieve. At first, it was simply an advantage in stamina and speed, helping them chase prey or escape danger. Later, it would allow some of their descendants to grow into the largest land animals the planet has ever seen. But in these early days, the dinosaurs were still experimenting with form and lifestyle. Some hunted insects and small vertebrates, darting among the roots of primitive forests. Others nipped at plants, beginning the experiments in herbivory that would later produce colossal long-necked feeders. They were opportunists, filling niches left vacant after the Permian collapse. In an ecosystem scarred by extinction, small, adaptable survivors had the best chances. Imagine the Triassic plains shimmering under a haze of heat. Sparse vegetation clings to the parched ground, and red rocks glow in the afternoon light. Out of the scrub darts a lithe, two-legged reptile, pausing just long enough to snap up an unwary lizard before vanishing into the shifting shadows. Its movements are quick, efficient, almost bird-like, though birds themselves are still over 150 million years in the future. For now, these tiny hunters and foragers are just another thread in a recovering world, and yet, in hindsight, they are the seeds of something extraordinary. From these modest beginnings will one day come the sauropods, with their sweeping necks, the plated stegosaurs, the crested hadrosaurs, and the great tyrants of the Cretaceous. In the Triassic, though, they were simply survivors, blending into a busy crowd of reptiles, amphibians and strange synapsids that still lingered from the Permian. It is worth remembering that not every reptile striding across the Triassic landscape was a dinosaur. In fact, most were not. Many creatures that look dinosaur-like in fossil form, armoured etosaurs, sail-backed phytosaurs, or fleet-footed Rauisuchians, belong to other lineages entirely. The early world was full of evolutionary experiments, some of them spectacularly odd. In a way, the Triassic was like nature's grand rehearsal, a stage where dozens of designs competed for staying power. Some lineages would vanish before the era was out. Others, like the small upright dinosaurs, would step quietly into the spotlight. And just to keep things in perspective, when picturing this era, try not to imagine every little reptile as a miniature Tyrannosaurus rex in training. Most of them were pursuing their own unique evolutionary paths, and only a few would leave descendants that truly reshaped the Earth. It is a gentle reminder that evolution is not a ladder leading to a single outcome, but more like a branching tree, with countless twigs cut short and others spreading into unexpected directions. In the fading heat of the Triassic day, as the first stars prick the sky above Pangaea, these early dinosaurs vanish into the shadows. They are not yet rulers, not yet giants, but their quiet steps echo into the deep future. What seems small and ordinary in this moment carries within it the blueprint of an empire that will last for more than 160 million years. The Triassic world eventually gave way to a new chapter in Earth's history, one that looked and felt very different. As the Jurassic period unfolded, the single supercontinent of Pangaea began to split apart. Great rifts opened across the land, carving valleys that would one day widen into oceans. The climate, though still warm, grew gentler in many regions. Where once there had been endless arid plains, now belts of moisture brought life in abundance. Rainfall nourished thick green forests, and entire landscapes transformed into what might be thought of as the world's first great garden. This was a land dominated by ferns, cycads, and towering conifers. Some of these conifers reached remarkable heights, forming canopies that stretched high above the ground, while beneath them thickets of ferns spread like carpets. The air was heavy with humidity, and in many places morning mists clung low, drifting between trunks and softening the edges of the landscape. To walk through these Jurassic forests would have felt like stepping into another world, verdant, quiet, and alive with creatures that would leave their mark in stone. Among the most extraordinary of these creatures were the sauropods. If the Triassic had been a world of small beginnings, the Jurassic was the era when dinosaurs truly tested the limits of size. Sauropods grew to lengths and heights unmatched by any other land animals before or since. With long necks stretching like cranes and bodies supported by sturdy column-like legs, they looked almost impossible, as though gravity itself had been bent to allow their existence. Yet their design was not only possible but efficient. Part of their secret lay in their bones. Sauropods possessed a system of air sacs connected to their lungs, much like the respiratory system of modern birds. This arrangement not only allowed for a highly efficient flow of oxygen through their bodies, but also lightened their skeletons. Their vertebrae, though enormous, were honeycombed with air spaces, reducing their weight without sacrificing strength. This gave them the ability to grow massive without collapsing under their own bulk. Their necks, too, were marvels of natural engineering, long and flexible, enabling them to sweep across wide areas of foliage without needing to move their bodies far. In these lush Jurassic forests, sauropods could feed continuously, stripping leaves from conifers, cycads, and ginkgos. It was a feeding strategy that matched the world's new abundance of plant life. Instead of competing with smaller herbivores over the same ground-level shrubs, they reached upward, turning treetops into vast buffet tables. Their sheer scale meant that few predators would dare approach them, and their herds could reshape the vegetation of entire regions. But not all dinosaurs chose the path of gigantism. While the sauropods stretched toward the sky, other lineages explored different possibilities. Feathered theropods began to appear, their bodies adorned with filaments that at first may have served for insulation or display. These early feathers, simple at first, would later become more complex, opening the door to new functions. The origins of flight were being quietly rehearsed, though true powered flight still lay ahead. In the Jurassic skies, early birds began to take tentative wing. One of the most famous is Archaeopteryx, discovered in the fine limestone of Germany. With its feathered wings and long bony tail, it bore a striking mixture of traits, half reptile and half bird. Though it could not soar like modern birds, it could glide and perhaps flap short distances, a preview of what was to come. These first experiments with flight mirrored the changes on the ground, a world of exploration where new forms of life tested new ways of being. Predators of the Jurassic also adapted to this lush world. Theropods diversified, some becoming swift hunters with long legs and grasping claws, others evolving into apex predators with powerful jaws. The balance of predator and prey played out across fern meadows and forest edges, with the thunder of sauropod herds often setting the rhythm of life. Smaller creatures thrived in the shadows. Early mammals no larger than shrews scurried through leaf litter, living cautious lives while giants strode above them. To imagine a morning in the Jurassic is to picture a conifer grove wrapped in mist. The rising sun sends pale shafts of light through the trees, and the air is heavy with the scent of damp foliage. In the distance, a deep vibration carries through the ground, the slow, deliberate steps of a sauropod moving unseen. Branches sway high overhead as it feeds, the sound soft and steady, blending with the call of feathered creatures stirring among the branches. This was a world of balance between enormity and delicacy, where the largest land animals ever to exist shared space with some of the smallest and most fragile beginnings of flight. The Jurassic Garden was not just a place of survival, but of experimentation, where life found new paths in the wake of change. From towering giants to fluttering forms with feathered wings, it was a time when the Earth's ecosystems grew deeper and more intricate, each layer adding to the harmony of an ancient living forest. The Cretaceous period marked one of the most profound shifts in the history of life on land. If the Jurassic was remembered as an age of giant forests and towering conifers, the Cretaceous brought an entirely new kind of greenery, flowering plants. Angiosperms, as they are known scientifically, began to spread across the continents, and in doing so they rewrote the rules of the ecosystem. With their blooms, fruits, and rapid growth cycles, they created opportunities for insects, herbivores, and eventually the predators that hunted them. Flowers were not just pretty ornaments of the landscape, they were evolutionary innovations. By attracting insects and other creatures to help spread their pollen, angiosperms established highly efficient partnerships that reshaped how plants reproduced and spread. Instead of relying solely on the wind or random chance, they enlisted armies of beetles, flies, and the earliest bees. The world became more colourful, more fragrant, and more intricately woven together. For the first time, the land carried a tapestry of blossoms and buzzing pollinators, a kind of quiet revolution beneath the feet of the dinosaurs. As the plants diversified, so did the animals that fed upon them. Hadrosaurs, often called the duck-billed dinosaurs, flourished during this time, with their flat, shovel-like snouts and hundreds of closely packed teeth forming enormous dental batteries. They were perfectly suited to grind the fibrous stems and leaves of flowering plants. Many hadrosaurs carried elaborate crests on their heads, some hollow and resonant like natural wind instruments. These crests may have been used for communication, producing deep calls that rolled across floodplains, allowing herds to keep in touch even when hidden by tall vegetation. Entire groups of these herbivores could move together, grazing fields of angiosperms much like modern herds of wildebeest sweeping across the savanna. Ceratopsians, the horned dinosaurs, also thrived in this flowering world. With their dramatic frills and intimidating horns, they were among the most visually striking animals to ever walk the earth. Beyond defence, those frills may have been billboards for display, their edges adorned with blood vessels that allowed them to flush with colour. A herd of ceratopsians moving across a plain of flowering plants would have been a sight of both power and beauty. Horns raised, frills shimmering in the sun, pollen drifting through the air like golden snow. Meanwhile, the great sauropods did not vanish. In the Cretaceous, they evolved into new forms, such as the titanosaurs, which became especially widespread in the southern continents. Titanosaurs roamed in herds across South America, Africa, and India, leaving behind trackways that stretched for kilometres. Some species reached lengths rivaling the giants of the Jurassic, their immense bodies supported by pillar-like legs as they browsed on trees and shrubs. Despite the rise of new herbivores, the titanosaurs continued to thrive, their sheer size keeping most predators at bay. This era was also a time of regional distinctiveness. As the supercontinent Pangaea continued to break apart, the continents drifted further toward their modern positions. Separated by growing oceans and inland seas, dinosaur populations became more localized. North America, for example, was split by a vast seaway that divided it into two landmasses, Laramidia to the west and Appalachia to the east. On Laramidia, a dazzling variety of dinosaurs evolved, many existing side by side in surprisingly high diversity. In Asia, new forms of feathered theropods appeared, some small and bird-like, others experimenting with flight in different ways. In the southern continents, titanosaurs dominated, while other lineages produced their own distinctive local forms. The Cretaceous was not a uniform stage but a patchwork quilt, each region developing its own character. The seas themselves were equally transformed. Vast inland oceans, such as the Western Interior Seaway, spread across the continents, creating long coastlines and shallow marine environments. These waters teemed with marine reptiles like mosasaurs, which became the apex predators of their ecosystems, as well as plesiosaurs with their long necks and swift fins. Schools of fish darted in the shallows, while ammonites floated in the open waters, their coiled shells recording the chemistry of ancient seas. Seabirds with toothy beaks skimmed the surface, while pterosaurs soared overhead, some with wingspans as wide as a small plane. Life in the Cretaceous was not confined to the land, but stretched across every environment the planet had to offer. Among the most striking developments of this time was the continued evolution of birds. Descended from small feathered theropods, the earliest true birds of the Cretaceous were refining the art of flight. Their wings grew stronger, their feathers more specialized, and their diversity greater. Some birds lived along shorelines feeding on fish, while others occupied forests, feeding on seeds or insects. Their presence was a reminder that not all dinosaurs were confined to the ground. With each generation, the boundary between bird and dinosaur blurred further, until one day the line would all but vanish. It is easy to imagine a Cretaceous morning on the edge of an inland sea. The air is filled with the hum of insects drawn to blossoms newly opened in the first light. Hadrosaurs shuffle quietly among the plants, grinding stems between their teeth while juveniles wander close by. A herd of ceratopsians raises their frilled heads, the colours of their crests glinting as they shuffle forward, pollen clouds catching the sunlight like flecks of gold. In the distance, the shadow of a titanosaur moves slowly, deliberate as a moving hill. Overhead, feathered forms flit between trees, while a pterosaur glides silently across the shoreline. It is not a world of monsters, but of endless interwoven lives, each dependent on the other. The Cretaceous tapestry was more than just a flourish of flowers and insects. It was the dawn of a new kind of interconnectedness, a preview of ecosystems that resemble the ones we know today. With flowering plants came fruits and seeds, opening niches that mammals and birds would later occupy. With insects came pollination networks that still underpin modern food webs. Dinosaurs, whether duck-billed grazers, horned defenders, or colossal titanosaurs, were part of this shifting picture, shaping and reshaping the land with every step. And yet, for all its beauty and complexity, the Cretaceous carried with it a sense of fragility. The ecosystems were rich, but they were also finely balanced, woven together like threads of silk. A disruption to one part of the web could ripple outward, affecting everything else. The golden snow of pollen drifting in the air symbolized both abundance and impermanence, a quiet reminder that even the grandest ages of life are temporary. The Cretaceous was a time of innovation, of flowering worlds and feathered wings, of seas filled with hunters and skies alive with new experiments. It was a time when dinosaurs reached their greatest diversity, when ecosystems grew as intricate as any before. And yet, in the drifting pollen and the gentle buzz of insects, there was always the whisper of change, a reminder that even this golden tapestry would one day unravel. When most people picture a dinosaur, they imagine the outside: teeth, claws, horns, and tails. But the true secret of their success lay within. The inner architecture of these animals tells a story of efficiency, endurance, and adaptability that allowed them to thrive for over 160 million years. For all their diversity, dinosaurs shared some remarkable internal traits that set them apart from the reptiles that came before them. One of the most striking features was their bone structure. Many dinosaurs had pneumatic bones filled with air sacs that connected to their lungs. At first glance, such bones might seem fragile, but this lightness was deceptive. Air-filled cavities strengthened their skeletons while reducing weight, making movement more efficient. Imagine a long-necked sauropod stretching 20 meters into the sky. Without such a system, its neck would have been impossibly heavy, dragging the animal down. With hollow, reinforced vertebrae, the neck became manageable, a natural crane sweeping across forests. These air sacs were more than just clever weight-saving tricks. They were part of a sophisticated respiratory system, one similar to the lungs of modern birds. Unlike mammals, which breathe air in and then out of the same passage, birds and dinosaurs had a unidirectional flow of air. Fresh oxygen moved continuously through their lungs, like water through a stream, ensuring a constant and efficient supply. This meant more oxygen could reach their muscles and organs, fueling activity at a level far beyond what sluggish reptiles could manage. In short, dinosaurs were built to be active. Evidence for this high-energy lifestyle appears in their bones themselves. Paleontologists study growth rings, microscopic lines laid down in bone tissue, a bit like the rings of a tree. In dinosaurs, these rings show rapid growth, especially in their youth. Some species went from hatchling to adult in just a few years, reaching enormous sizes at a pace that would be impossible for a cold-blooded reptile. This rapid growth required a fast metabolism, a constant intake of food, and an internal engine working at high speed. Isotopes preserved in fossil bones and teeth add to the picture. These chemical signatures reveal clues about body temperature and metabolic rates. In many dinosaurs, the data suggest elevated, stable body temperatures, more like birds and mammals than modern reptiles. They were not basking, slow-moving creatures that relied entirely on the sun to warm them. They generated and maintained heat internally, keeping their bodies ready for bursts of movement, long migrations, or the demands of raising young. The question of whether dinosaurs were warm-blooded or cold-blooded has stirred debates for decades. The truth seems to be both more complex and more interesting. Dinosaurs were not simply one or the other, but something in between, or perhaps something entirely their own. Some scientists describe them as mesothermic, a metabolic middle ground that allowed flexibility. This meant they could sustain higher activity than reptiles while avoiding the enormous energy demands of mammals. A calm way to phrase it might be, not hot, not cold, but beautifully in between. How dinosaurs managed body temperature is another piece of the puzzle. Feathers are the most famous solution. Once thought to belong only to birds, feathers are now known to have been present in many non-avian dinosaurs as well. At first, these were simple, hair-like filaments, excellent for insulation. Over time, feathers became more complex, branching into veins and quills, eventually serving for display and flight. In smaller dinosaurs, feathers trapped warmth, helping them maintain steady body temperatures in cooler conditions. Other dinosaurs experimented with very different tools. Stegosaurs carried large plates along their backs, while sail-back species like Spinosaurus displayed tall structures supported by spines. For a long time, paleontologists suggested these acted like radiators, surfaces for absorbing or releasing heat. Modern studies show the story may be more complicated. Blood vessels did run through such structures, but they could also have been for display or intimidation. A row of plates or a towering sail could serve both practical and social functions, just as antlers or manes do today. The truth may lie in a mixture, structures shaped by both physiology and the pressures of survival. Even body size itself played a role in thermoregulation. Large animals changed temperature slowly, a concept known as thermal inertia. Sauropods, for example, may have maintained relatively constant body temperatures simply because their massive bodies resisted rapid changes. Small dinosaurs, on the other hand, would have relied more heavily on feathers or other coverings. The variety of solutions reflects the enormous diversity of dinosaur life, from tiny bird-like forms to immense, mountain-sized herbivores. All of these internal adaptations supported behaviours that pushed dinosaurs far beyond the limits of their ancestors. An efficient respiratory system allowed sauropods to grow into living skyscrapers, breathing enough oxygen to power their massive frames. High growth rates fueled rapid development, letting hatchlings grow quickly out of danger. Elevated metabolic strategies gave predators the stamina to pursue prey, and herbivores the energy to migrate across landscapes in search of food. These were not sluggish creatures dragging themselves through swamps, but dynamic, active animals. It is worth pausing here to reflect on how much of this knowledge comes not from direct observation, but from careful study of fossils. A slice of bone under a microscope, the shape of an air cavity, the chemical trace left in ancient enamel. Each is a clue, a whisper of how these animals lived inside their own skins. Piece by piece, the puzzle comes together, showing not just skeletons but beating hearts, flowing blood, and deep breaths that once filled ancient lungs. There is something almost poetic in imagining a dinosaur breathing. Air passes through sacs, flows across lung tissue, and cycles onward, never stagnant, always moving. The system is elegant, economical, and enduring. So enduring, in fact, that it still exists today in the birds singing outside modern windows. When one hears the call of a sparrow or the cry of a hawk, one is also hearing the echoes of a system perfected in the age of dinosaurs. So the next time the debate arises, were dinosaurs warm-blooded or cold-blooded, the answer can be given with a quiet smile. They were neither, or perhaps both. They were something different, a reminder that life does not always fit into the neat boxes we prefer. Evolution often takes the middle path, or creates entirely new ones. Dinosaurs lived in that space, thriving with bones that breathed, bodies that grew at astonishing speeds, and metabolisms tuned to a rhythm uniquely their own. What moved inside them was just as impressive as the forms they displayed on the outside. Their physiology was not hidden weakness, but hidden strength. The unseen machinery that carried them through more than 160 million years of history. To picture them only as teeth and claws is to miss half the story. They were marvels of biology from the inside out, creatures whose very bones tell us they were made for life in motion. For a long time, the image of dinosaurs was painted in scales and leathery hides. They were imagined as giant lizards, their skin rough and reptilian, draped over immense skeletons. But discoveries over the last few decades have shown that this picture was only part of the truth. Dinosaurs were far more diverse in their outer coverings than once believed, ranging from pebbly scales to filaments, and in many cases to complex feathers that rival those of modern birds. The earliest evidence of feathers appears in small theropods, the group that would eventually give rise to birds. At first, these feathers were simple filaments, sometimes called protofeathers. They were little more than hair-like structures branching out from the skin in a loose fuzzy covering. To the eye, these protofeathers would have given a dinosaur a slightly downy appearance, softening its outline and perhaps making it look more mammal-like than reptilian. Such filaments likely appeared in multiple dinosaur lineages, not just the ancestors of birds, which suggests that feather-like structures were a deeper, more widespread trait than once thought. As evolution continued, feathers grew more complex. From single filaments came branching forms, with barbs splitting from a central shaft. Eventually, some dinosaurs developed vanned feathers with interlocking barbules, the kind of structure we see in modern flight feathers. These later feathers were not just for insulation, but also for display, aerodynamics, and even tactile functions. The progression shows a gradual layering of utility, from keeping warm to signalling to others, to perhaps carrying creatures into the air. Scales never vanished, however. Many dinosaurs carried both scales and feathers in different parts of their bodies. Some had scaly tails with feathered arms, others bore patches of both depending on their lineage. This mosaic of integuments reminds us that evolution does not replace one system entirely with another. Instead, it tinkers and mixes, keeping what works and experimenting with new designs. The outer covering of dinosaurs was not uniform but varied, flexible, and often surprising. One of the most exciting areas of study in recent years has been the investigation of fossilized melanosomes, the tiny pigment-bearing structures within feathers and skin. Under powerful microscopes, paleontologists have identified these microscopic traces in exquisitely preserved fossils, especially those from sites in China. The shape and density of melanosomes correlate with colours in living birds, allowing scientists to make cautious inferences about the colours of ancient feathers. A dinosaur with elongated, sausage-shaped melanosomes might have had dark, glossy feathers, while spherical ones might suggest browns or reds. These discoveries have given rise to striking reconstructions. A small dromaeosaur called Anchiornis has been proposed to have carried a pattern of black and white feathers with a hint of red cresting its head. Other species may have had iridescent sheens, their feathers catching the light in shifting colours much like starlings or hummingbirds today. Yet it is important to treat these findings with care. Fossilization is a delicate process, and not all pigments preserve equally. What we see in melanosomes is often only part of the story. The full vibrancy of a dinosaur's colours, including structural colours created by microscopic feather patterns, may remain beyond our reach. Still, even these cautious glimpses are enough to reimagine their world as anything but drab. Rather than dull grey giants, the Mesozoic was alive with stripes, crests, and displays, a riot of colours and textures designed not for our eyes but for the eyes of other dinosaurs. Feathers, in this sense, were not just blankets of warmth, but also flags of communication. The functions of feathers and filaments were as diverse as their forms. Insulation was an early and obvious advantage. Small dinosaurs, especially those with higher metabolisms, needed to keep their body temperatures stable. A coating of filaments trapped heat close to the body, much like the down feathers of a chick. In cooler climates, this would have been essential for survival. Display was another critical role. Bright crests, patterned wings, and elaborate tails could all serve as signals to mates, rivals, or members of the same species. Just as peacocks today spread their tails in dazzling fans, so too might dinosaurs have flaunted their feathers. The frills of ceratopsians and the crests of hadrosaurs remind us that visual signalling was common in many lineages, and feathers offered an even wider canvas. Some feathers may have served as sensory tools. In modern birds, specialised feathers detect subtle changes in airflow, helping them adjust during flight. In dinosaurs, feathers along the arms or tails might have heightened awareness of surroundings, adding sensitivity in the same way whiskers do for mammals. This suggests a level of tactile sophistication often overlooked in reconstructions. The interplay between function and form extended across species. In one setting, feathers might have meant warmth, in another they meant showmanship, in yet another they carried the animal into the air. Evolutionary biology thrives on such versatility. Structures rarely serve a single purpose for long. They adapt, shift, and acquire new uses as conditions change. The feather is one of the most vivid examples of this principle. Beginning as a simple filament and blossoming into an array of tools and ornaments. To imagine the quiet intimacy of these coverings, picture a small dromaeosaur at dusk. The air is cooling, and the last light of the sun slants low across the forest floor. The dinosaur sits still for a moment, its head turning this way and that. Then, with delicate precision, it begins to preen, drawing its beak along each feather, aligning barbs and shaking loose bits of dust. Each motion is both instinct and necessity, a way of keeping feathers clean, aligned, and effective. If one could watch unseen, it would feel oddly familiar, so much like a sparrow at the edge of a modern garden, carrying out the same ritual inherited across millions of years. That scene reminds us that dinosaurs were not alien monsters, but living animals, each invested in the care of their bodies and the signals they sent to the world. Their coverings were not only functional, but expressive, part of their identity and survival. In feathers and filaments, in scales and skin, they carried the marks of evolution's patience, weaving warmth, colour, and meaning into every contour. The legacy of those coverings is still alive today. Every bird that flits through the air is a continuation of that ancient experiment. The feathers on a robin's breast or the shimmer of a pigeon's neck are echoes of structures first grown by creatures that lived tens of millions of years ago. The colours, the displays, the soft down of a chick, they are not merely bird traits, they are dinosaur traits, carried forward in time, proof that the age of dinosaurs never truly ended. When thinking of the largest creatures to ever walk the earth, the mind inevitably turns to the sauropods. These giants, with their impossibly long necks and massive bodies, were living mountains that reshaped the ecosystems around them. They're not only remarkable for their size, but for the engineering that made such size practical, even graceful. Instead of collapsing under their own bulk, sauropods moved with surprising efficiency, their design a masterpiece of evolutionary problem-solving. The first challenge was simply support. Sauropods bore their immense weight on legs built like pillars. These columnar limbs functioned less like the flexible joints of most animals, and more like the sturdy beams of architecture. Straight, vertical, and powerful, they distributed weight directly down to the ground, minimizing stress on the bones. A titanosaur weighing over 70 tons could stand firm because its skeleton worked like a cathedral of living bone, channeling forces down through each pillar to the earth below. Yet these legs were not stiff tree trunks. Evidence from fossil trackways shows that sauropods could walk steadily, with a rolling, rhythmic stride that carried entire herds across landscapes. Their necks were perhaps their most famous feature. Stretching sometimes longer than the body itself, these necks allowed sauropods to browse across a wide area without needing to move their huge frames. A single individual could sweep its head in graceful arcs, stripping leaves from trees at different heights. The bones of these necks were ingenious, vertebrae honeycombed with air spaces that made them surprisingly light for their size. Instead of dragging a crushing weight, the sauropod neck was a flexible air-filled crane, supported by strong muscles and balanced by a powerful tail. This arrangement meant they could access food in ways no other herbivore could, reaching high into the canopy or low to the ground without shifting their massive bulk. But sauropods did not live in isolation. Fossil evidence paints a picture of social animals, moving in groups across plains and valleys. Trackways show parallel footprints of multiple individuals travelling together, suggesting coordinated herds. Nesting grounds have also been found, vast sites where dozens or even hundreds of sauropods laid eggs in shallow pits. These communal nesting areas imply not only social behaviour, but also a life cycle that depended on numbers. Hatchlings were tiny compared to their parents, often no bigger than a human baby when they first cracked open their shells. Growing from such fragile beginnings to titanic size required both rapid growth and strategies for survival in a dangerous world. Growth rates in sauropods were astonishing. Bone studies show that juveniles grew quickly, reaching large sizes within a few decades. This rapid pace was essential, as small hatchlings would have been easy prey for the many predators of their time. By accelerating growth, sauropods could move out of the most vulnerable stages of life more swiftly. Once they reached even a fraction of their adult size, their bulk alone became their best protection. Few predators would risk tangling with a creature the size of a bus, let alone one the size of a building. Diet was another puzzle. To sustain bodies weighing tens of tons, sauropods needed vast amounts of food, yet the plants available to them were not particularly rich in calories. Conifers, cycads, and ferns dominated their world, and these were fibrous, low-quality meals compared to modern flowering plants. The solution was scale. Instead of chewing their food to a pulp as many herbivores do, sauropods swallowed large mouthfuls of leaves and let their enormous guts handle the processing. Their digestive systems acted as giant fermentation chambers, where bacteria broke down tough plant matter over long periods of time. By eating continuously and in huge volumes, sauropods could survive on resources that would starve smaller animals. It was less about quality and more about quantity, a strategy summed up by a playful bedtime reminder: eat your greens, sauropod style. Despite their immense size, sauropods were not clumsy behemoths. Their skeletons were lightened by air sacs, their limbs built for efficiency, and their stride steady and balanced. They were not sprinting hunters, but neither were they lumbering in misery. Instead, they were creatures perfectly adapted to the demands of gigantism. Their size was not a liability, but an advantage. It allowed them to reach untapped resources, deter predators, and shape entire ecosystems through their feeding. Imagine the sight of a herd crossing a Jurassic floodplain at dawn. The ground trembles faintly with each step, yet the movements are steady and unhurried. Necks sway in wide arcs as the animals graze, heads lifting occasionally to scan the horizon. Juveniles move among the legs of adults sheltered within the group. The air is filled with the sound of leaves tearing from branches, the low rumble of calls, and the rhythmic thud of colossal feet pressing into the earth. Their presence would have transformed landscapes. Entire forests could be reshaped by the constant feeding of sauropod herds. Vegetation patterns shifted under their grazing, with plants evolving strategies to cope with their appetite: tougher leaves, higher growth, or rapid regeneration. In turn, sauropods moved across regions in search of new food, creating cycles of disturbance and renewal that echoed across millions of years. They were not passive occupants of their world, but active engineers, influencing the very structure of ecosystems. Lifespan is more difficult to pin down, but many scientists believe sauropods could live for many decades, perhaps even a century in some cases. Their steady growth and resilience suggest long lives, punctuated by the seasonal rhythms of migration, nesting, and feeding. In this sense, they were not unlike elephants today, shaping their environment not only through sheer size, but also through the accumulated presence of long-lived individuals. To us, sauropods often appear as impossibilities. How could anything so large exist on land without collapsing or starving? And yet they did, for tens of millions of years. Their design was not accidental, but refined, honed by evolution into a combination of strength, lightness, and endurance. They remind us that nature does not always work within the limits we imagine. With the right adjustments, even the heaviest of giants can move with grace. So the next time you picture these immense creatures, think not of clumsy monsters but of elegant engineers, each step a balance of physics and biology. Their bones were airy yet strong, their limbs columns of living stone, their necks sweeping arcs of possibility. And through it all, they carried on with the simple but powerful strategy of eating plants on a scale few creatures could match. Giants, yes, but giants with grace. Among the many wonders of the dinosaur world, few creatures capture the imagination quite like the ceratopsians and the ankylosaurs. These were not sleek predators or towering sauropods, but animals defined by their ornaments and their armour. Where some dinosaurs relied on speed or size, these lineages turned to horns, frills, plates, and clubs, features that made them both spectacular to look at and highly effective in the struggle for survival. Their bodies became canvases of evolutionary creativity, blending defense, display, and social signals into living works of art and engineering. The ceratopsians, a group that flourished in the Cretaceous period, are perhaps the most recognizable horned dinosaurs. The most famous among them is Triceratops, with its 3 formidable horns and massive frill. But Triceratops was just one member of a vast family. From smaller early relatives like Protoceratops to flamboyant species such as Styracosaurus, with its crown of spikes, ceratopsians showcased an astonishing variety of headgear. Their skulls were among the most elaborate ever produced by vertebrate evolution. At first glance, horns and frills seem straightforward. They look like weapons and shields. Indeed, a Triceratops horn could pierce with deadly force, and a solid frill could absorb blows from a predator. Fossil evidence of punctures in skulls suggests that these dinosaurs did not shy away from confrontation. Yet the story is richer than combat alone. The frills were not merely slabs of bone but living structures with blood vessels running close to the surface. This means they could have flushed with colour, turning pale shields into vivid displays. In the same way that a peacock raises its tail or a lizard extends its throat fan, a ceratopsian might have used its frill to catch the eye of rivals and mates alike. The diversity of frill shapes hints strongly at display as a driving force. Some species sported wide, solid shields, while others carried frills pierced with holes or adorned with elaborate spikes. These differences were often species-specific, suggesting that frills may have acted like identification cards, helping individuals recognize members of their own group. In a world filled with herds and rival populations, clear visual signals would have been valuable. It is not difficult to imagine a plain dotted with grazing ceratopsians, their frills rising like banners in the sunlight, each pattern a declaration of identity. Horns too were multi-purpose tools. They could certainly be dangerous, as predators like Tyrannosaurus rex would have discovered if they chose the wrong target. But within species, horns may have been equally important for social interactions. Many ceratopsian skulls show signs of healed injuries, possibly from head-to-head clashes much like the sparring of modern bison. Such contests would not necessarily have been fatal, but could have helped establish dominance, settle disputes, or win the attention of potential mates. A herd of horned dinosaurs may have been as much a society of competitors and signallers as it was a defensive unit. If ceratopsians were the ornamented knights of the dinosaur world, ankylosaurs were the living tanks. These low-slung, heavily armoured herbivores carried their defences across their backs in the form of osteoderms, bony plates embedded in the skin. Arranged in rows and patterns, these plates created a formidable shield that turned the ankylosaur's body into an armoured fortress. Some species went even further, evolving tail clubs made of fused bone that could swing with devastating force. A predator facing an ankylosaur risked not only a mouthful of armour, but also a bone-cracking strike from behind. The armour of ankylosaurs was not uniform. Some had relatively small, simple plates, while others developed elaborate spines, ridges, and even eyelid protection. In certain species, the osteoderms were so large and complex that they became almost like mosaics, each plate fitting into the next in a patchwork of defence. This arrangement provided not only physical protection but also visual deterrence. A predator looking for an easy meal would think twice when confronted with a creature that resembled a walking shield wall. There is evidence to suggest that ankylosaurs did not rely on armour alone. The tail clubs of some species were heavy and well-muscled, capable of delivering crushing blows. Computer models show that these clubs could break bones, which means they were not just for show. Whether used against predators or in contests with other ankylosaurs, they were powerful tools that added another layer of security to an already formidable body plan. It is hard not to admire the sheer practicality of such design. Low to the ground, armoured on top and armed with a weapon at the rear. Yet even these heavily armoured creatures were more than their defences. Fossil sites containing multiple individuals suggest that ankylosaurs, like ceratopsians, may have lived in groups. Their armour would have been impressive in herds, a moving landscape of plates and clubs, reinforcing the sense of safety in numbers. For predators, such gatherings would have been daunting obstacles, each individual a challenge and the group as a whole nearly impenetrable. The social lives of these dinosaurs are glimpsed in other ways as well. Bone beds containing large numbers of ceratopsians point to herding behaviour. In some cases, the individuals within these bone beds range from juveniles to adults, suggesting family groups moving together. Growth studies of ceratopsian skeletons show distinct changes in horn and frill shape as animals matured, much like antlers in deer. Juveniles had smaller, simpler structures that grew more elaborate with age, likely signalling readiness for adulthood and reproduction. This life stage progression highlights the importance of ornaments not only in defense, but also in the rhythms of social life. The interplay between ornament and armor tells us that dinosaurs were not simply locked in a battle for survival against predators. They were engaged in complex interactions with each other. Horns and frills were as much about communication as they were about combat. Armor and clubs were as much about deterrence as they were about direct fighting. These features reveal lives filled with signaling, competition and display, a richness often hidden when we think only of dinosaurs as prey or predator. To imagine them is to picture not just conflict, but quiet scenes as well. Picture a moonlit plain where a herd of ceratopsians rests. Their silhouettes rise against the silver glow, the outlines of frills and horns catching the light. Nearby, the slow shapes of ankylosaurs move in the shadows, their backs glinting faintly with armoured ridges. It is not a world of constant violence, but of presence, of creatures living and breathing in societies shaped as much by communication and signal as by the need for protection. The ornaments and armour of ceratopsians and ankylosaurs remind us that evolution often works with more than one purpose in mind. What begins as defence can become display, what starts as a warning can become a signal of attraction, and what looks like mere ornament can turn out to be essential to survival. In these dinosaurs, bone became both shield and canvas, carrying messages across millions of years. Even in silence, their frills and plates still speak, whispering of herds beneath the sun and of horns and armour glinting in the moonlight. If ceratopsians were the armoured knights of the Cretaceous, then hadrosaurs were the great orchestras of their age. These so-called duck-billed dinosaurs dominated northern continents in the late Cretaceous, shaping ecosystems not with horns or armour, but with teeth, voices and complex social lives. To imagine their world is to imagine vast herds grazing across floodplains, their calls echoing over wetlands, each note rolling like the sigh of wind through reeds. Hadrosaurs earned their nickname from the broad, flat beaks that capped their jaws. These beaks were not designed for snapping branches or crushing bone, but for cropping vegetation with precision. Behind the beak, however, lay their true secret weapon, the dental batteries. Each hadrosaur jaw carried hundreds of teeth arranged in tightly packed columns. As old teeth wore down, new ones slid into place, creating an endless conveyor belt of chewing surfaces. With these dental batteries, hadrosaurs could grind plants with remarkable efficiency. In fact, their chewing ability has been compared to that of modern grazing mammals like horses or cows, a far cry from the simple up-and-down bites of earlier dinosaurs. This innovation allowed them to thrive on the fibrous, tough plants that filled Cretaceous landscapes, from conifers and ferns to the newly flourishing flowering plants. Some hadrosaurs evolved elaborate cranial crests, hollow structures that curved and twisted in extraordinary ways. Species like Parasaurolophus carried long, backward-sweeping tubes, while others sported domes, ridges, or hatchet-shaped crests. These structures were not mere decorations. The hollow passages within them functioned as resonating chambers, turning breath into deep, far-carrying calls. Paleontologists using computer models have reconstructed the possible sounds of these dinosaurs, and the results are haunting. Low, rumbling tones, almost like the notes of an enormous wind instrument. The purpose of these sounds likely range from communication within herds to signalling species identity. In a world filled with many different hadrosaur species, each crest shape could have corresponded to a unique voice, ensuring that calls were recognized even at great distances. Males and females may have used these calls during courtship, and parents may have used them to keep track of their young in dense groups. It is a reminder that sound has always been one of life's great connectors, binding individuals together across space. Evidence for hadrosaur social behavior is strong. Fossilized nesting grounds reveal large colonies where many individuals laid eggs in close proximity. Some nests contain signs of repeated use over generations, suggesting that hadrosaurs return to the same sites year after year, much like modern seabirds. The arrangement of nests indicates organised spacing, as though each pair maintained a small territory within the colony. Within the nests, delicate eggshells and tiny skeletons show that hatchlings stayed in place for some time before venturing out. This points to parental care, with adults likely bringing food or guarding their young until they were strong enough to join the herd. Trackways provide further insight. Long lines of footprints show herds moving together, sometimes with smaller prints, probably juveniles, walking in the shelter of larger adults. These tracks stretch for kilometers, suggesting migration across vast landscapes. Moving as a unit would have provided safety, food security, and the benefits of many eyes watching for predators. The herd itself became a kind of living fortress, with the vulnerable kept safe at its heart. Hadrosaurs also displayed a striking degree of adaptability. They lived in a range of environments, from warm coastal plains to cooler high latitudes where long winters brought months of darkness. Some populations may have migrated seasonally, while others endured the polar night by feeding on whatever vegetation was available. Their success across such varied conditions speaks to their versatility, both as individuals and as groups. Despite their reputation as gentle giants, hadrosaurs were not defenseless. Herd behavior offered strong protection, and their sheer size was enough to deter many predators. An adult Parasaurolophus or Edmontosaurus could weigh several tons, making it a challenging target. When threatened, herds may have responded with coordinated movement, with deep calls reverberating across the marshes as warning signals. In such moments, their voices were not only tools of social bonding but also alarms carrying urgency through the group. To envision their world is to imagine a wetland at dusk. The air is heavy with the scent of mud and water plants. A herd of hadrosaurs moves slowly, tearing at reeds with their broad beaks. Their crests rise like strange sculptures against the horizon. Then, a low note drifts out, deep and rolling, followed by another and another, until the air hums with resonance. It is not chaotic, but harmonic, a choir of breath and bone echoing across the water. The sound is steady, almost meditative, a lullaby carried by giants of the Cretaceous. The mastery of food processing, the orchestration of sound, and the dedication to family life all made hadrosaurs some of the most successful herbivores of their time. They demonstrate that survival does not depend only on sharp teeth or heavy armor, but can be achieved through cooperation, communication, and patience. They turned the plants of their world into energy with unmatched skill, and they turned their crests into voices that bound herds into communities. In the end, hadrosaurs remind us that dinosaurs were not just solitary figures battling for existence. They were social beings, invested in their young, responsive to each other's calls, and organized into societies that left their mark on the land. Their footprints, nesting sites, and resonant crests tell the story of animals that thrived not by isolation, but by connection. And as night settles over the wetlands, their low calls still seem to drift through the imagination, deep and wind-like, rolling gently into silence, a choir of duck-billed giants, singing softly across time. When people imagine dinosaurs, their minds often leap first to the predators, sleek, sharp-toothed hunters sprinting across plains, claws flashing, jaws snapping shut with bone-crunching force. And while that image is partly true, it is only one side of a much richer picture. Theropods, the great predatory branch of the dinosaur family tree, were astonishingly diverse, ranging from small, nimble chasers no larger than a dog to apex giants that dominated their ecosystems. Their strategies for survival were as varied as their shapes, and while some were built for raw power, others thrived through speed, precision, or adaptability. Theropods can be loosely divided into two broad categories: gracile and robust forms. The gracile hunters were built for speed and agility. Long legs, lightweight bodies, and sharp claws gave them the ability to dart and slash with deadly accuracy. Dinosaurs like Velociraptor and Troodon fell into this category. Their skeletons reveal adaptations for quick turning, fast bursts of movement, and a keen sense of balance. The robust theropods, by contrast, were heavyweights. With thick skulls, massive jaws, and bone-crushing teeth, they relied less on agility and more on sheer force. Allosaurus in the Jurassic and Tyrannosaurus rex in the Cretaceous epitomize this build. Where gracile hunters were scalpels, robust predators were hammers. One of the most striking features of theropods was their vision. Many species had forward-facing eyes, granting them binocular vision and depth perception. This ability to judge distances accurately was invaluable for hunting. Unlike reptiles that rely largely on smell or heat, theropods could focus on prey, track its movement, and strike with precision. In some cases, the field of vision may have overlapped so well that they could see in 3 dimensions much as hawks or owls do today. For an animal with sharp teeth and fast reflexes, this was a formidable advantage. Theropods also possessed an impressive toolkit of claws and bite forces. Gracile species carried sickle-shaped claws on their feet, curved and sharp, perfect for slashing at prey. Their hands often bore long, grasping claws that could pin or slice. Robust species invested more in jaws. Tyrannosaurus rex had one of the most powerful bites in the history of land animals, capable of crushing bone with forces exceeding several tons. Fossil evidence of tooth marks in bones shows that these predators did not just tear flesh, but chewed through skeletons to access the marrow inside. Each strategy, claws or crushing jaws, spoke to the variety of evolutionary solutions to the problem of predation. The question of how theropods hunted is a matter of continuing debate. Did they operate cooperatively, like wolves, or were they solitary opportunists? Evidence exists on both sides. Trackways of smaller theropods sometimes suggest coordinated movement, raising the possibility of group hunting. Fossil assemblages of multiple individuals have also fueled speculation that some species may have hunted in packs, working together to bring down larger prey. On the other hand, these gatherings could represent accidents of preservation or individuals drawn to a common food source. With fossils, the difference between a coordinated hunt and a crowd at a carcass is not always clear. What is certain is that theropods were flexible. They could take advantage of whatever opportunities arose, whether that meant chasing down live prey, scavenging from carcasses, or perhaps doing both as circumstances allowed. The old image of predators as purely hunters and scavengers as separate roles has largely been set aside. Modern predators blur those lines, and theropods likely did too. A Tyrannosaurus rex might scavenge a carcass one day and actively hunt the next. To them, meat was meat, whether moving or not. The fossil record shows bones with both healed and unhealed bite marks, suggesting that these dinosaurs were capable hunters but also ready scavengers when the chance arose. In the end, labeling them as either-or misses the reality of nature. Survival rarely plays by strict categories. Theropod behaviour also carried layers of nuance often overlooked in popular imagery. For example, smaller species like Troodon had unusually large brains for their size, suggesting problem-solving abilities or complex behaviours. Some may have used sharp senses to forage at night, hunting under moonlight when larger predators rested. Others may have relied on ambush rather than pursuit, blending into vegetation before launching sudden strikes. Fossilized stomach contents and tooth marks on prey bones reveal diets ranging from insects and small vertebrates to large herbivores. The strategies were as varied as the animals themselves. Their silence is another intriguing thought. Unlike mammals, dinosaurs did not have vocal cords in the way we do. Some may have produced low, resonant sounds through air sacs connected to their respiratory systems, much like birds today. Others may have communicated with hisses, bellows, or even closed-mouth booming sounds. The hollow crests of hadrosaurs show how sound could be amplified, and theropods may have had their own methods of making their presence known. Yet in the fossil record of footprints, silence reigns. Each print is a reminder that not every trackway records a dramatic chase. Sometimes it was just a dinosaur walking by, minding its own business. Not every footprint means a chase scene, though it is tempting to imagine them that way. Predators lived lives of tension and opportunity. A gracile hunter might stalk through the undergrowth, eyes fixed forward, every muscle coiled for a strike. A robust giant might lumber toward a watering hole, its bulk alone sending smaller creatures scattering. The strategies differed, but the goal was always the same: find food, conserve energy, and survive long enough to pass on genes. Even the mightiest predator lived under the same rules of hunger and necessity that govern life today. To picture them is to imagine landscapes filled not just with colossal roars, but with moments of quiet intensity. A shadow moving among ferns, a ripple of water as a clawed foot steps into a stream, the sudden stillness before the burst of motion. Predators were not always locked in combat with their prey. More often they were waiting, calculating, and conserving energy, their strategies unfolding as silently as the night itself. In their diversity and adaptability, theropods demonstrate that predation was not a single story, but a spectrum of possibilities. From swift hunters with slicing claws to bone crushers with monumental jaws, they occupied nearly every niche of carnivory. Their legacy continues in the birds of today, many of which still carry sharp beaks, keen eyes, and a flair for opportunism. The age of dinosaurs was not ruled by one predator, but by 1,000 strategies, each tuned to the rhythms of its time. And in the end, their silent footsteps remind us that power can take many forms, not all of them loud. Few creatures in Earth's history command as much fascination as Tyrannosaurus rex. Its very name, Tyrant Lizard King, has become shorthand for raw power, a title that evokes an image of thunderous footsteps, massive jaws, and a predator unrivaled in its world. Yet the allure of T-Rex is not simply its size or its teeth. It is the way all its traits came together. An animal built not just bigger but differently, a predator honed to extraordinary efficiency. The first thing that set T-Rex apart was its sensory arsenal. Fossils of its skull show enormous olfactory bulbs, the regions of the brain dedicated to processing smell. These were proportionally larger than in almost any other dinosaur, suggesting that T-Rex could track scents over vast distances. A carcass miles away may have been detected on the breeze, guiding the tyrant lizard through forests and floodplains toward its next meal. Its vision was equally impressive. With forward-facing eyes, T-Rex possessed binocular vision, allowing precise depth perception. The size of its optic nerves and the structure of its skull suggest eyesight sharper than that of hawks today. It was not the half-blind, lumbering brute once depicted in early films, but a predator that could spot movement and focus on detail with deadly accuracy. Add to this an acute sense of hearing, with inner ear structures tuned to low-frequency sounds, and you have an animal equipped to perceive its environment in ways that made prey detection and communication second nature. Then there were the jaws. The bite force of T-Rex has been estimated at over 6 tons, strong enough to crush solid bone. Fossilized remains of hadrosaurs and ceratopsians often bear puncture marks that match the teeth of T-Rex, some of which show signs of healing. This means that not only did T-Rex bite with astonishing force, but its prey sometimes survived encounters, carrying the scars of its attacks. Other bones show no healing at all, evidence of successful kills or scavenging. Unlike predators that sliced flesh into strips, T-Rex could pulverize skeletons, extracting marrow and nutrients that other carnivores might have left behind. It was an eater of entire carcasses, a recycler as much as a hunter. Yet this immense power was balanced by an unusual life history. Studies of bone growth rings show that T-Rex went through extraordinary teenage growth spurts. For several years, individuals may have gained more than 1,000 kilograms annually, surging from gangly juveniles to towering adults. Juvenile tyrannosaurs were built differently from their elders: longer legs, lighter frames, and narrower jaws. These features suggest a different ecological role, perhaps chasing smaller prey at speeds adults could not match. As they matured, their proportions shifted, the limbs thickening, the skull widening, and the bite force multiplying. In this way, a single species filled multiple niches during its life, with teenagers and adults hunting in different ways and on different prey. This flexibility extended to its range. T-Rex dominated western North America during the late Cretaceous, inhabiting regions from forests to coastal plains. Fossils show it coexisted with hadrosaurs and ceratopsians, two of the most abundant herbivores of the time. These plant eaters provided a steady food supply, whether through hunting or scavenging. A herd of duck-billed hadrosaurs offered the chance for pursuit, while a ceratopsian carcass offered the promise of bone-cracking feasts. The tyrant did not need to specialize when abundance surrounded it. Despite its legendary reputation, T-Rex was not invincible. Broken bones and healed injuries in fossils tell us it lived a life of conflict and hardship. Some specimens show evidence of disease, including parasitic infections that may have affected the throat, making feeding difficult. Others bear deep bite wounds, possibly from clashes with other tyrannosaurs. The life of the tyrant was one of survival, not effortless dominance. Yet its adaptations meant that even in the face of struggle, it remained the apex predator of its ecosystem. The fascination with T-Rex also lies in its duality. It was both terrifyingly powerful and scientifically nuanced. Its tiny arms, once mocked as useless, were actually strong and muscular, capable of gripping during feeding or mating. Its huge tail provided balance, allowing surprising agility for such a massive animal. Every feature carried purpose, and together they created not a caricature of brute force, but a finely tuned organism. To picture T-Rex is to imagine a predator at once brutal and elegant, a colossal head swinging low over the body, jaws lined with teeth the size of bananas, eyes that could track movement with precision, nostrils twitching at the faintest scent, legs striding with deliberate power, and yet, behind the image of the roaring giant is also the juvenile, lean and quick, sprinting after smaller prey in its teenage years. It was an animal that changed with age, filling roles across its lifetime, and always leaving its mark on the landscape. As with all dinosaurs, T-Rex was part of a larger web. Its existence was tied to the abundance of herbivores, the fertility of the land, the shifting climates of the late Cretaceous. Its power did not make it independent of these forces, but intertwined with them. In the end, even the tyrant was subject to the same fate that overtook all dinosaurs at the close of the Cretaceous. Its reign, though mighty, was finite, and yet the fascination endures. More than a century after its discovery, T-Rex continues to inspire awe, research, and imagination. It is the poster child of the dinosaur age not just because it was big, but because it was extraordinary in every measure: senses, strength, adaptability, and presence. Imagine then the close of a day in the Cretaceous, Clouds gather over a floodplain, and rain begins to fall in soft, steady sheets. A tyrannosaur stands alone, its silhouette massive against the dimming light. Droplets run down the contours of its skull as it lowers its head toward the ground, nostrils twitching at a distant scent. Each breath mingles with the sound of rain tapping on leaves and water pooling in the soil. For a moment, the tyrant lizard king is quiet, not in pursuit, not in combat, but simply a creature in its world, as rain whispers over the land it once ruled. When we try to imagine the inner lives of dinosaurs, the evidence is faint but fascinating. Bones and teeth tell us much about their size and diet, but what about their senses, their daily rhythms, and even their moments of rest? With careful study of fossil skulls, trackways, and nesting grounds, scientists are beginning to glimpse what it might have been like to experience the world as a dinosaur. It is a quieter story than roaring battles or thunderous stampedes, but perhaps a truer one, filled with perception, movement, and the need for sleep. One of the most revealing sources of information comes from endocasts, impressions of the inner spaces of dinosaur skulls where their brains once sat. By creating molds or scanning these cavities, paleontologists can estimate the relative size and shape of different brain regions. While dinosaurs did not have brains as large as mammals of comparable size, certain features stand out. In many theropods, the optic lobes were well developed, suggesting keen vision. Olfactory bulbs were often enlarged, especially in predators like Tyrannosaurus rex, pointing to a powerful sense of smell. These impressions are like fingerprints of behavior, clues that reveal whether sight, smell, or hearing dominated a dinosaur's world. The inner ear provides another set of clues. Tiny bony structures preserved in fossils indicate how dinosaurs balanced and what kinds of sounds they could hear. The semicircular canals of the inner ear, which help animals orient themselves in space, were especially well developed in fast-moving theropods, implying quick reflexes and agile movement. Hearing ranges can also be inferred from the shape of the cochlea, the part of the ear that processes sound. Many dinosaurs appear to have been sensitive to low frequencies, capable of detecting deep rumbles that carried across long distances. Such sounds may have been ideal for communication in open landscapes, where a low call could travel farther than a high-pitched one. These sensory adaptations tie closely to social life. Trackways, long chains of fossilized footprints, sometimes show groups of dinosaurs moving together in parallel lines. These records of ancient journeys suggest coordinated herding, with individuals adjusting their pace to match. In some cases, smaller footprints appear beside larger ones, hinting at young moving alongside adults. The picture that emerges is not of solitary wanderers, but of social creatures navigating the landscape in company. Their senses, sight to follow movement, smell to recognize kin, and hearing to detect calls, would have been vital in keeping such groups together. Nesting colonies add to this image of social complexity. Fossil sites reveal dozens, sometimes hundreds, of nests clustered in close quarters. Eggs are arranged carefully, often in circular patterns, suggesting deliberate construction rather than random scattering. In some species, hatchlings remained in the nest for days or weeks, their small bones preserved alongside eggshell fragments. Adults likely guarded or fed their young, behaviours that imply a degree of parental care. To raise offspring in colonies requires coordination and tolerance, the ability to live among neighbours without constant conflict. The fossil record suggests dinosaurs managed this balance, creating societies where the young could grow within the safety of the group. But what of their daily rhythms? Did dinosaurs, like modern animals, follow cycles of activity and rest? Evidence here is subtler. The structure of fossilized eyes, specifically the scleral rings that support the eyeball, can reveal whether a species was adapted for day, night, or twilight activity. Some dinosaurs, particularly smaller theropods, show adaptations consistent with nocturnal or crepuscular lifestyles, hunting under the cover of dim light. Herbivores, meanwhile, may have mixed feeding with rest, grazing during cooler hours and resting when the sun was strongest. These patterns suggest a division of labour across the day and night, spreading activity across the cycle of 24 hours. And yes, even the giants likely needed naps. While it is difficult to imagine a 70-ton sauropod settling down for a snooze, rest would have been as necessary for them as for any other animal. Perhaps they dozed standing, or shifted their weight onto the ground for brief periods, the herd keeping watch while individuals rested. Smaller dinosaurs may have curled into sheltered spots, tucking heads beneath arms like modern birds. Sleep is one of the life's constants, and there is little reason to believe the age of dinosaurs was exempt from it. One could almost say, with a hint of playfulness, that even giants needed their naps. Behavioural hints extend further in signs of play and social interaction. Bite marks on fossils sometimes come not from hunting but from sparring, practiced duels between individuals of the same species. Uneven wear on bones may indicate repetitive movements, as though some dinosaurs engaged in ritualized displays. In the fossil record, these behaviours appear only as subtle traces, but when pieced together, they suggest animals not unlike those of today, creatures that competed, displayed, courted and raised young with energy and intention. To step back, it is striking how much of this story is built not on complete skeletons but on fragments. The curve of an ear canal, the angle of a trackway, the shape of a nest. Each fragment is a quiet voice speaking across millions of years, telling us that dinosaurs were not simply monsters of size but animals with senses, rhythms and societies. They listened, they watched, they smelled the air, they followed one another across landscapes, and they paused to rest beneath the rising or setting sun. If we imagine them at night, a new perspective emerges. The moon rises over a plain where a herd of hadrosaurs settles near water. Some keep their heads raised, nostrils twitching, while others lower themselves into stillness. A low call drifts across the group, answered softly in return, a way of saying, all is well. In the distance, a predator pauses, listening, gauging whether to approach or to move on. And then, for a time, quiet settles in. Even in the age of dinosaurs, there were moments of calm, moments when societies rested under the same stars we see today. Dinosaurs were not just bones and teeth. They were living beings shaped by senses, patterns and connections. Their brains may not have been large by our standards, but they were suited perfectly to their needs. They could balance, navigate, communicate and raise families. And when the day's demands were done, they too would have closed their eyes and let the world drift by, reminding us that even in the Mesozoic, life followed the steady rhythm of waking and sleeping. The Mesozoic was not only the age of dinosaurs on land. The oceans and skies carried their own rulers, equally strange and equally spectacular, though technically not dinosaurs at all. While herds of ceratopsians grazed the plains and sauropods swept their necks through forests, other reptiles claimed the air above and the seas below. Together they created a world filled with teeth and wings, long necks and spiraled shells, a stage of life more diverse than any one group could hold. In the oceans, plesiosaurs and mosasaurs reigned supreme. Plesiosaurs, with their long necks and paddle-like limbs, looked like something out of a dream. Their bodies were sleek, designed for graceful movement through the water. Some species carried impossibly extended necks, with dozens of vertebrae strung together like beads. These creatures swam with a slow, almost ethereal grace, their four flippers beating in unison like the wings of a bird underwater. Others in the plesiosaur lineage developed shorter necks and massive heads, trading elegance for power, their jaws lined with sharp teeth for seizing slippery prey. Then came the mosasaurs, who emerged later in the Cretaceous and quickly became apex predators of the seas. Related not to plesiosaurs but to monitor lizards, mosasaurs showed how evolution often arrives at similar solutions through different paths. With elongated bodies, paddle-like limbs, and tails shaped for propulsion, they moved like scaled torpedoes. Fossils show they reached immense sizes, some stretching over 15 meters. Their skulls reveal jaws capable of opening wide, aided by double-hinged joints and flexible skull bones, allowing them to swallow large prey whole. Fish, turtles, seabirds, and even other marine reptiles all fell into their menu. They were the sharks of their day, roaming warm, shallow seas that covered much of the continents. Their prey included ammonites, marine mollusks with coiled shells patterned in spirals. Ammonites were abundant and diverse, each shell marking time like a spiral clock. Many carried intricate ridges and patterns, as if evolution had sketched endlessly on their shells. Their extinction at the end of the Cretaceous was profound, but during the Age of Reptiles they were everywhere, their forms drifting in the currents like floating ornaments of the sea. Above the oceans, pterosaurs filled the skies. These flying reptiles were the first vertebrates to master powered flight, long before birds or bats. Their wings were made of membranes stretched over elongated finger bones, a design unlike anything that came before or after. Some were small, flitting over coastlines and lakes in search of fish or insects. Others were vast, reaching wingspans of 10 meters or more, their shadows sweeping across beaches and lagoons. Quetzalcoatlus, one of the largest known pterosaurs, rivaled a small plane in size. To see such a creature lift off would have been like watching a sail come alive and drift into the air. Many pterosaurs carried elaborate head crests, some shaped like sails, others tall and narrow, some curved like scythes. The functions of these crests remain debated. They may have played a role in flight stability, but many scientists believe they were signals, visual displays for mating, recognition, or intimidation. In this, pterosaurs paralleled the frills of ceratopsians and the crests of hadrosaurs. Across land, sea, and air, creatures were sculpted not only by survival, but by the demands of communication and beauty. Their wings required immense adaptation. The bones of pterosaurs were light yet strong, filled with air spaces like those of birds. Muscles anchored to their chests powered their flight strokes, while membranes stretched between their bodies, wings, and even legs, creating control surfaces for maneuvering. They were not simply gliders, but capable flyers, soaring on thermals, diving with precision, and covering vast distances. The skies above the Mesozoic seas were alive with their movements, their cries echoing over waves. The presence of these reptiles alongside dinosaurs reveals the richness of the Mesozoic tapestry. Land was not the only theatre of innovation. In the oceans, plesiosaurs and mosasaurs solved the challenge of aquatic life in different ways, one with elegant necks and steady flippers, the other with streamlined speed and crushing jaws. In the skies, pterosaurs experimented with crests, sizes, and strategies, filling niches from small insect hunters to ocean-fishing giants. Each group was distinct, yet all thrived under the same sun, shaped by similar pressures of feeding, mating, and moving through their environments. For all their differences, they shared convergent designs: flippers, streamlined bodies, soaring wings. Life kept arriving at solutions that worked, even when starting from different beginnings. Evolution, it seems, writes variations on themes, finding echoes in water, air, and land alike. To imagine this world at rest is to picture starlight glittering on calm waves, the ocean surface dark and smooth. Beneath, the shapes of plesiosaurs drift like shadows, their long necks weaving through silver schools of fish. Far below, a mosasaur glides, its body undulating with power, jaws opening wide for an ammonite caught unaware. Overhead, wings pass silently, the silhouettes of pterosaurs gliding across the stars. The land may have belonged to the dinosaurs, but the seas and skies were no less alive, no less extraordinary. These creatures remind us that the age of reptiles was not a single story, but a symphony of different movements. The dinosaurs ruled the land, but they shared their time with neighbours just as dramatic, giants of the deep and rulers of the wind. Together they filled Earth with motion and sound, with wings above and teeth below, in oceans that shimmered and skies that soared. And for a moment in deep time, the world belonged to them all. Every fossil is a whisper from deep time, a fragment of a story that once played out in full, but now survives only in scattered traces. To learn about dinosaurs and their world, scientists rely on those whispers, teasing meaning from bones, footprints, and even grains of sediment. It is a process that blends patience, precision, and imagination, turning the hard labour of digging and the quiet work of microscopes into a portrait of vanished lives. The journey often begins in the field. Fossils do not present themselves neatly on the surface. Paleontologists scour badlands, cliffs, and deserts, where erosion exposes the right kinds of rocks. Hours or days might pass without a single find, until at last a hint of bone appears in the soil, a pale fragment gleaming against the matrix of stone. From there, excavation begins with the simplest of tools, brushes, picks, even dental instruments. Each stroke must be careful because the fossil may be fragile after millions of years underground. What emerges is wrapped in plaster jackets to protect it on the long journey back to the laboratory. Preparation in the lab is a different kind of patience. The rock encasing the fossil must be removed grain by grain, often under a microscope. Specialized tools, sometimes as fine as sewing needles or as precise as air-powered chisels, allow technicians to reveal structures without damaging them. This stage can take weeks, months, or even years. A skull may sit half buried on a workbench while its preparator slowly frees the delicate bones from their stone cradle. It is a reminder that deep time cannot be rushed. Once prepared, fossils can be studied with modern imaging techniques that peer inside without cutting them open. Computed tomography scans, or CT scans, use X-rays to build three-dimensional images of fossils in extraordinary detail. These scans reveal hidden structures, the paths of air sacs in bones, the shape of inner ears, even the tiny chambers inside teeth. In some cases, digital models allow researchers to reconstruct entire skeletons, testing how joints moved or how skulls withstood forces. What once required speculation can now be measured in data, thanks to machines that can look through stone itself. Histology adds another layer. By cutting thin slices of bone and examining them under microscopes, scientists can see growth rings much like those in trees. These rings record the rhythms of life, seasons of plenty when growth was rapid, lean years when it slowed, the rapid surges of youth and the steady pace of adulthood. Histology tells us not only how old a dinosaur was when it died, but also how fast it grew and how its metabolism was tuned. A cross-section of bone is both a relic and a diary, carrying traces of a life lived millions of years ago. But fossils are not perfect records. Taphonomy, the study of how organisms decay and become preserved, reminds us of the biases in what we find. Most creatures never become fossils at all. Soft tissues rot, bones are scattered by scavengers, floods wash remains away, and many bodies vanish without leaving a trace. Only under specific conditions, burial in sediment, protection from scavengers, the right chemistry, do remains become preserved. This means the fossil record is partial and uneven, a collection of rare survivals rather than a complete census. Some species may be lost to time entirely, while others are known only from fragments. To fill these gaps, paleontologists combine multiple lines of evidence. Stable isotopes preserved in bones and teeth can reveal what dinosaurs ate or what climates they lived in. Oxygen isotopes, for example, can suggest body temperatures or seasonal patterns in water sources. Carbon isotopes may indicate whether an animal fed on particular kinds of plants. Sedimentology, the study of the rocks surrounding fossils, places them in context. Riverbeds, floodplains, deserts or coastlines. Grain size, mineral composition, and layering tell the story of the landscape where the fossil was buried. From these threads emerges paleoecology, the attempt to reconstruct entire ecosystems. A single fossil becomes part of a wider picture. Predators and prey, plants and climate, rivers and seas. A ceratopsian skull is not just a skull. It is evidence of grazing herds, of predators that pursued them, of the plants that fed them, and the climate that shaped them. To build these pictures requires collaboration between geologists, chemists, biologists, and more, each adding a piece of the puzzle. The process is one of patience at every stage. The patience of searching barren ground for a fragment of bone, the patience of freeing fossils from stone, the patience of interpreting signals written in isotopes and sediments, and the patience of weaving together incomplete evidence into a story that is both careful and imaginative. Science advances by resisting the urge to leap too quickly, by waiting for the rocks to reveal what they hold. It is humbling to realize how much of our knowledge comes from so little. A footprint pressed into ancient mud can reveal how a herd moved together, the spacing of their steps recording size, speed, and behavior. A nest of eggs can whisper of parenting and social bonds. A broken tooth in a bone can tell of predator and prey, of a struggle long vanished. These traces are whispers, fragile and faint, but powerful in what they reveal. Imagine standing in a windswept badland where the rocks are striped with bands of colour. Beneath your feet lies the record of entire worlds, pressed into stone across millions of years. Most of it is silence, but here and there are whispers, bones, tracks, shells, pollen grains. To hear them requires not just tools and techniques, but the willingness to listen with care. In that sense, paleontology is as much an act of patience as it is of discovery, waiting for deep time to yield its secrets, one quiet fragment at a time. The world of the dinosaurs was shaped not only by bones and behaviour, but also by the climates in which they lived. To step into the Mesozoic is to step into a greenhouse Earth, a planet where carbon dioxide levels were often several times higher than today, where sea levels rose and fell with shifting tectonic plates, and where continents were arranged in ways that created strange patterns of weather. Dinosaurs, pterosaurs, and marine reptiles were not simply creatures of anatomy, they were also creatures of climate, moulded by heat, humidity, and long cycles of change. At the dawn of the Mesozoic, the supercontinent Pangaea stretched like a colossal puzzle piece across much of the globe. With so much landmass gathered into one, the interior of Pangaea was vast and dry. Moisture from the oceans struggled to reach far inland, leaving deserts and arid plains. Early dinosaurs like Eoraptor and Herrerasaurus scurried across sun-baked landscapes, where heat shimmered off red rocks and vegetation clung to rivers and oases. It was a time of extremes, when summers were blistering and winters could be surprisingly cold for those far from the moderating effect of the sea. As the Jurassic period unfolded, Pangaea began to break apart. Rifts widened into seaways, and the climate shifted with them. Moisture returned to regions once parched, and lush belts of green spread across the land. The rise of ferns, conifers, and cycads created a patchwork of forests, while great river systems crisscrossed valleys. The air was thick with humidity, carrying the calls of early birds and the low rumbles of sauropods moving through groves of towering trees. Rain fell often, feeding the growth of dense vegetation, and with it came the expansion of herbivores that could feed on endless greenery. High carbon dioxide levels kept the planet warm, with little to no permanent ice at the poles. Instead of icy wastelands, the polar regions were covered in forests. Fossil wood and leaves from Antarctica and the Arctic tell of ecosystems filled with trees adapted to long months of summer daylight and long months of winter darkness. These were not barren, frozen realms, but thriving. Green landscapes where dinosaurs grazed beneath canopies of dawn redwood and ginkgo. To live here required remarkable resilience. Imagine enduring 4 months of near-constant sunlight, followed by 4 months of twilight gloom, with food supplies waxing and waning in strange rhythms. Dinosaurs in these regions likely migrated, hibernated, or developed strategies to endure the swings of light and dark. Elsewhere, climate patterns shaped life in other dramatic ways. Evidence suggests that seasonal monsoons drench some regions, with heavy rains followed by long dry spells. Trackways in ancient mudflats show herds moving across landscapes that may have alternated between flood and drought. Animals would have adapted by timing migrations with rainfall, following water and fresh vegetation. In this sense, dinosaurs were not so different from elephants and wildebeest of today, bound to the cycles of weather and the turning of the seasons. Sea levels, too, played their part. At times in the Cretaceous, the oceans rose so high that shallow seas spread across entire continents. Much of what is now North America lay beneath the western interior seaway, a warm, shallow ocean that stretched from the Arctic to the Gulf of Mexico. Along its shores, hadrosaurs browsed and nested, while plesiosaurs and mosasaurs hunted in the waters. Inland seas created coastlines thousands of kilometers long, reshaping habitats and providing opportunities for both marine and terrestrial life. These seaways were rich with ammonites, fish and seabirds, adding complexity to the food webs that sustained dinosaurs at the edges of the land. The warmth of the Mesozoic also allowed plant life to flourish in abundance. Flowering plants appeared during the Cretaceous, diversifying rapidly and reshaping ecosystems. Their spread was linked not only to the evolution of pollinators, but also to the consistently warm, humid climates that encouraged their growth. Forests became more varied, prairies of low vegetation spread in patches, and herbivores adapted their diets accordingly. The success of ceratopsians and hadrosaurs, with their specialized teeth, was tied to this botanical revolution. But a world this warm was not without challenges. Heat demanded adaptation. Dinosaurs may have regulated body temperature through a mix of behavior and anatomy. Large plates on stegosaurs, frills on ceratopsians, sails on spinosaurids, all may have played roles in thermoregulation, catching breezes or radiating excess heat. Smaller dinosaurs, especially those with feathers, could have used their coverings as insulation during cool nights, or as shading during hot days. There were no jackets in the Mesozoic, but there was plenty of shade in the form of forests, and plenty of clever anatomy to balance the warmth. It is important to note that Mesozoic climates were not uniform. Local environments varied widely, from arid deserts with sparse vegetation to tropical swamps buzzing with insects. Fossils preserve this diversity. Petrified wood from lush forests, ripple marks from shallow seas, and mud cracks from drying lakes. Dinosaurs were not confined to one narrow niche. They thrived across a mosaic of conditions, adapting their behaviors to the climates they encountered. Reconstructing these climates is a feat of science in itself. Geologists and paleoclimatologists use chemical signatures in rocks and fossils to measure past carbon dioxide levels and temperatures. Oxygen isotopes in fossilized shells can reveal the warmth of ancient seas. Plant fossils record not only species but also growth patterns, which change with temperature and rainfall. Together, these clues create a picture of a world where warmth and humidity were the rule, but with enough variation to shape evolution in surprising ways. When we imagine the age of dinosaurs, we often think of colossal bodies and toothy jaws. Yet those lives unfolded against a backdrop of sun and rain, forests and deserts, seas and polar twilight. Climate was the stage, setting the rhythms of growth, migration and survival. Dinosaurs adapted not just to each other but to a planet in flux, finding ways to live in a greenhouse world. Picture the close of a long day in the Cretaceous. The air is thick with moisture, cicadas hum among the ferns, and the horizon glows with the colours of a humid sunset. Herds gather in the cooling evening, resting after hours of feeding. In the distance, forests stretch endlessly, green and alive, under a sky without ice caps. It was a world of warmth, where the climate shaped giants and small creatures alike, and where survival meant learning to thrive beneath sun, storm and shade. Dinosaurs may capture the imagination with their size and strength, but beneath their every step lay the true foundation of their world, the plants that sustained them. Without forests, ferns and flowering meadows, there would have been no herds of hadrosaurs, no towering sauropods, and no grazing ceratopsians. The age of dinosaurs was also, in its own quiet way, the age of plants, an era when greenery spread, changed and adapted, shaping not just the landscapes but the creatures that lived upon them. In the Triassic and early Jurassic, the land was dominated by gymnosperms, the naked seed plants that predated the rise of flowers. Conifers stretched upward into towering forests, their resin-scented needles catching sunlight high above the ground. Cycads, with their thick trunks and crown of stiff leaves, grew in groves, their silhouettes looking strangely palm-like though they were not palms at all. Ginkgo trees, with their fan-shaped leaves, stood resilient in scattered patches, a lineage that survives to this day as living fossils. Ferns and horsetails carpeted the ground, filling spaces between the giants. Together, these plants created layered habitats, with high canopies, shaded understories and dense ground cover where smaller animals could hide. These plants were more than background scenery. They shaped dinosaur diets and behaviours. Early herbivores browsed conifers and cycads, stripping needles, gnawing tough fronds, and grinding fibrous tissues that required powerful jaws and complex teeth. The digestive systems of dinosaurs were closely tied to the greenery available to them. Large sauropods with their enormous guts could process vast amounts of low-quality plant matter, while hadrosaurs and ceratopsians evolved intricate dental batteries to tackle tougher leaves. The plants pushed back too, evolving defences such as spines, tough tissues and chemical compounds to make themselves less appealing meals. This back and forth between plants and herbivores is one of the great co-evolutionary stories of the Mesozoic. By the Cretaceous, a revolution was underway. Flowering plants, angiosperms, appeared and spread rapidly across the globe. With them came a new diversity of shapes, scents, and seeds. Unlike gymnosperms, which relied heavily on wind for pollination, many flowering plants forged relationships with insects and other pollinators. Fossil evidence shows that beetles, flies, and early bees were already playing their roles in these ancient ecosystems. The arrival of flowers added bursts of colour and variety to the Mesozoic landscape, creating new opportunities for herbivores and reshaping diets once more. Dinosaurs that had long fed on conifers and cycads now had access to fresh foods, softer leaves, fruits and seeds. This shift in plant life also influenced how forests were structured. Cretaceous ecosystems became more complex, with dense undergrowth of flowering shrubs beneath coniferous canopies. Forest edges grew lush with flowering plants, providing seasonal resources that may have guided migrations and feeding habits. Just as modern deer follow seasonal blooms, herbivorous dinosaurs may have tracked the spread of angiosperms across valleys and plains, their movements tied to the rhythms of plant reproduction. Fire was another factor in these ancient landscapes. High levels of oxygen in parts of the Mesozoic meant that wildfires were more common than we might imagine. Charred plant remains in fossil deposits show that flames occasionally swept across forests, clearing underbrush and opening space for new growth. Some plants were adapted to this cycle, sprouting quickly after burns or carrying seeds that thrived in newly cleared soil. Dinosaurs living in these regions would have encountered a mosaic of freshly burned ground, regrowing shoots, and mature forest, each stage providing different opportunities for feeding. In this way, even fire played its role in the balance between plants and animals. Plant defences were as creative as they were persistent. Cycads, for example, developed toxins in their tissues, making them less appetizing to many herbivores. Ferns produce spores in great numbers, overwhelming grazers with sheer abundance. Angiosperms added thorns and spines to stems and branches, an evolutionary arms race in miniature. Yet dinosaurs adapted just as swiftly. Their sheer size gave some the ability to eat plants that smaller creatures could not handle. Their jaws and teeth evolved to slice, grind, and crush. Some species may even have developed gut microbes that neutralize toxins, just as modern herbivores use microbes to help digest cellulose. The dance between eater and eaten was as intricate as any predator-prey relationship, though slower, subtler, and spread across centuries. It is striking to consider how much plants shaped the great evolutionary paths of dinosaurs. The ability of sauropods to grow to immense sizes was tied directly to the abundance of conifer forests that could supply endless quantities of foliage. The success of hadrosaurs and ceratopsians in the Cretaceous was tied to their mastery of flowering plant diets. Predators, too, felt the influence of plants indirectly, for the distribution of herbivores dictated where tyrannosaurs and dromaeosaurs would hunt. The greenery of the world set the stage for every other act. Paleobotanists, scientists who study fossil plants, piece together these stories from leaves, pollen grains, and petrified wood. Tiny spores preserved in sediments act like time capsules, drifting from the past to reveal what kinds of plants thrived at different times. Pollen grains, in particular, are remarkably durable, their tough wool surviving for hundreds of millions of years. Under a microscope, they reveal the rise of flowering plants, each grain a delicate sculpture frozen in time. In this way, even the smallest traces tell of revolutions that reshaped entire continents. Imagine a quiet Mesozoic forest. The canopy sways with the weight of conifers, their resinous scent heavy in the air. Beneath them, cycads spread their crowns of stiff leaves, and ginkgo leaves fan in the breeze. Ferns cover the ground, their spores drifting upward like dust motes in shafts of light. In the distance, the first flowering shrubs open their blooms, visited by humming insects. A herd of hadrosaurs passes, cropping plants with efficient beaks and leaving trampled trails through the undergrowth. Every step they take is guided by what grows around them, every bite tied to the slow but relentless pulse of photosynthesis. The plants of the Mesozoic did not simply support dinosaurs. They shaped them, challenged them, and coexisted with them in complex ways. They built the green worlds through which giants moved, worlds of shade and spore, of towering trunks and tiny seeds. And when the day was done, when the herds rested and the predators grew still, those same plants continued their quiet work, feeding on sunlight, releasing oxygen, and scattering spores like whispers into the air. They remind us that even in an age of titans, the true rulers of the earth were often rooted in place, growing patiently, one season at a time. The story of dinosaurs is not just about towering adults striding across ancient landscapes. It is also a story of beginnings, eggs buried in soil, fragile hatchlings taking their first steps, and young dinosaurs finding their place in the herds and forests of the Mesozoic. To understand these creatures fully, one must look not only at the skeletons of giants, but also at the delicate traces of reproduction, growth, and care that reveal how life was renewed again and again for over 160 million years. Eggs are among the most evocative fossils we have. Rounded, elongated, or slightly flattened, they range from the size of a pigeon's to larger than a rugby ball, depending on the species. Some were laid singly, others in carefully arranged clutches. Fossil nests show patterns that suggest deliberate placement, as if parents took time to position their offspring's first homes. In certain sites, dozens of nests appear in close proximity, evidence of colony nesting. These colonies hint at a social side to reproduction, with many individuals gathering in the same place to lay eggs, guard nests, and perhaps increase survival through sheer numbers. The discovery of brooding dinosaurs has added new depth to this story. Fossils of oviraptorids have been found crouched protectively over their nests, wings outstretched in postures remarkably similar to modern birds. This suggests that some dinosaurs did not simply abandon their eggs, but actively guarded them, keeping them warm and safe. The connection to birds becomes all the clearer in these moments, when one realizes that behaviors as familiar as nesting and brooding stretch back into the deep past. Once hatched, young dinosaurs faced enormous challenges. Their bones, studied through histology, reveal rapid growth rates. Thin slices of fossil bone show growth rings, much like those of trees. These rings indicate bursts of growth in early years, when juveniles needed to reach a safer size quickly. Some species show astonishing growth spurts. A hadrosaur or sauropod might grow from a hatchling small enough to fit in your hands to a subadult weighing hundreds of kilograms within a few short years. This pace of growth speaks to elevated metabolisms and diets rich enough to sustain such expansion. But juveniles were not just miniature versions of adults. They often occupied different ecological niches, reducing competition within their own species. A young sauropod, for example, may have fed on low vegetation, while adults with long necks reached the canopy. Juvenile tyrannosaurs were slender and fast, chasing smaller prey, while adults became massive bone crushers capable of tackling ceratopsians. This partitioning of roles allowed entire populations to thrive, with each life stage contributing differently to the ecosystem. Evidence for juvenile care and protection adds even more texture. Trackways sometimes show groups moving together, with smaller footprints nestled among larger ones. This suggests herds that sheltered their young within the group, much as modern elephants do. Nesting grounds provide further hints. In some sites, young dinosaurs remained in nests long enough to grow teeth suited for chewing, implying they were fed or at least protected until they could leave. Parental investment, whether through guarding, feeding, or leading, may have been more common than once thought. The eggs themselves hold subtle stories. Their shells preserve microscopic structures that can be analysed for clues about nesting environments. Some shells suggest eggs were buried in vegetation, their warmth supplied by rotting plant matter, much like crocodiles today. Others appear adapted for open-air nests, perhaps shaded and guarded. The texture of the shell, the size of the pores, and the arrangement of the clutch all speak to strategies of reproduction shaped by climate, environment, and evolutionary history. The survival of young dinosaurs was, of course, precarious. Fossilized nests often contain broken shells alongside tiny skeletons, signs that not every hatchling made it far. Predators would have been drawn to colonies, where eggs and chicks offered easy meals. In this sense, the life of a baby dinosaur was both fragile and precious, balanced between the dangers of the world and the efforts of parents and herds to protect them. Yet enough survived to continue the line for millions of years, proof of the success of these strategies. Growth did not stop at hatching. Some dinosaurs reached sexual maturity long before they were fully grown. A tyrannosaur, for example, may have been capable of reproducing in its teenage years while still growing rapidly toward adult size. This strategy ensured that even in a world filled with hazards, individuals could pass on their genes before reaching old age. Growth rings in bones confirm this accelerated pace, painting a picture of animals that grew fast, bred young, and lived in cycles tuned to survival. The variety of strategies across species was immense. Some laid large clutches of eggs, relying on numbers to ensure survival. Others laid fewer but invested more in care. Some built nests in colonies, while others may have hidden their eggs in secluded spots. The diversity of reproductive strategies mirrored the diversity of dinosaurs themselves, proving there was no single dinosaur way of raising the next generation. If we could stand at a nesting ground at dawn, the scene would be both familiar and strange. The air is cool, mist rising off the ground. Dozens of nests dot the earth, each a circle of eggs nestled in soil or lined with vegetation. Adults move carefully among them, some lowering their bodies to brood, others standing guard. Tiny hatchlings poke their heads above the rim of a nest, blinking at the first light of day. In the distance, the low calls of a herd rumble through the air, a reminder that even the youngest are part of something larger. It is a quiet moment, filled with the beginnings of lives that may grow into giants, predators, or graceful grazers. Reproduction and growth reveal dinosaurs not as static figures, but as living beings caught in the cycles of birth, youth, maturity, and death. Their eggs, nests, and bones speak of care, struggle, and survival strategies as varied as the animals themselves. For every towering skeleton in a museum, there was once a fragile egg in the soil, a hatchling testing its legs, and a young dinosaur finding its place in a dangerous world. These beginnings, repeated across generations, ensured that dinosaurs did more than exist. They thrived, filled the planet, and carried their legacy forward until the end of their reign. The world of the dinosaurs was not a single, uniform landscape stretching endlessly from pole to pole. It was a patchwork of regions, each with its own cast of creatures, shaped by drifting continents, rising seas, and the flow of rivers and deserts. Biogeography, the study of how life is distributed across space and time, reveals that the age of dinosaurs was filled with provincial worlds, places where unique lineages thrived in isolation, or where local environments sculpted distinct communities. The story of dinosaurs is as much about geography as it is about anatomy. One of the clearest examples of this comes from late Cretaceous North America, where the western interior seaway divided the continent into two long strips of land. To the west lay Laramidia, a narrow stretch pressed between the seaway and the mountains. To the east was Appalachia, a larger but more isolated landmass. Fossils from Laramidia paint a picture of extraordinary diversity, with hadrosaurs, ceratopsians, ankylosaurs, and tyrannosaurs coexisting in dynamic ecosystems. Appalachia, however, preserved a different story, where lineages evolved separately, cut off from the Western world by the vast inland sea. This division highlights how geography acts as a gatekeeper of evolution. When populations are separated, they begin to diverge, creating unique forms adapted to local conditions. Farther south, the continents of Gondwana were drifting apart. South America, Africa, Antarctica, India, and Australia once formed a connected landmass, but as they pulled away from one another, their dinosaur faunas began to diverge. In South America, titanosaurs rose to prominence, some reaching extraordinary sizes, while in Africa, spinosaurids with their crocodile-like snouts prowled river systems. India, drifting northward, carried its own distinctive dinosaurs, including abelisaurids, before colliding with Asia. Australia's record reveals smaller, polar-adapted species that braved long periods of darkness. The slow drift of continents acted as a storyteller, guiding lineages into new environments and encouraging them to adapt in ways that made each region distinct. Islands, too, wrote their own chapters. Isolation on small landmasses often produced dwarf forms, where limited resources favoured smaller body sizes. On islands in what is now Europe, sauropods and other dinosaurs shrank dramatically compared to their mainland relatives. This phenomenon, known as island dwarfism, is seen in many animal groups across history, from mammoths on Wrangel Island to deer in the Mediterranean. In the Mesozoic, it created miniature versions of giants, creatures that carried the grandeur of their lineage in reduced frames. These dwarfed species remind us that evolution is as much about limits as it is about possibilities. Rivers played another central role in shaping dinosaur life. Many fossil-rich sites are ancient floodplains, where periodic flooding deposited sediments that buried bones, footprints, and plant remains. These river systems supported lush vegetation, attracting herds of herbivores and the predators that hunted them. The dynamics of rivers, changing channels, seasonal floods, and fertile soils created habitats rich in diversity. Fish, amphibians, reptiles, and birds mingled with dinosaurs along the water's edge, forming ecosystems as complex as modern savannas or wetlands. A river valley was not just a geographic feature, it was a lifeline, providing food, water, and routes of migration. Deserts, by contrast, offered challenges that forced adaptation. Fossils from arid environments reveal species that lived with scarce vegetation and shifting sands. In some regions, evidence of dune fields and dry basins suggests that dinosaurs endured climates of extreme heat and drought. Herds may have migrated across vast distances in search of water, while predators shadowed them through barren landscapes. The contrast between fertile river valleys and arid deserts demonstrates how regional differences shaped behaviours, diets, and survival strategies. Coastal regions added another layer of variety. Along ancient shorelines, dinosaurs lived side by side with marine reptiles, seabirds, and invertebrates. The presence of tidal flats and estuaries created habitats that combined land and sea, where herbivores browsed vegetation growing in fertile deltas and predators lurked near water. In these transitional zones, fossils often preserve a blend of life. Dinosaur tracks alongside shells, bones mingled with driftwood, and impressions of plants adapted to brackish water. Inland communities, by contrast, show a different composition. More terrestrial specialists, fewer marine influences, and ecosystems dominated by forests and plains. These contrasts between inland and coastal, island and continent, north and south, remind us that dinosaurs were not a single global population, but a collection of regional worlds. Each environment sculpted its own communities, and each community added richness to the story of the Mesozoic. When we look at the fossil record, these distinctions are not just scientific curiosities, they are essential to understanding why diversity flourished. The separation of land masses encouraged experimentation, isolation forced adaptations to local conditions, connectivity allowed for mixing, competition, and exchange. Together, these forces created a dynamic balance where life was constantly being reshaped by the contours of the Earth itself. It is easy to think of dinosaurs in universal terms, a sauropod here, a ceratopsian there, as if they roamed interchangeable landscapes. But the truth is more textured. A hadrosaur in Laramidia lived a different life than a dwarf sauropod in an island forest, or a spinosaurid in a river delta. These creatures were as much products of geography as of biology. Their lives were framed by coastlines, rivers, deserts, and mountain ranges, by the slow but relentless drift of continents across millions of years. Picture for a moment the variety. In the west of ancient North America, herds move across a narrow strip of green land between sea and mountains, their calls rising over the sounds of crashing waves. In the south, on a fragmenting Gondwanan continent, a titan towering over the trees feeds on endless foliage, while spinosaurids stalk the shallows nearby. Across an island chain, smaller dinosaurs pick their way through groves of cycads, dwarfed but no less adapted to their patch of earth, and in the far north, a forest rests under weeks of daylight, where herds prepare for the long stretch of polar night. The continents drifted, rivers shifted, seas rose and fell, and deserts spread. Through it all, dinosaurs adapted, filling niches as varied as the landscapes themselves. Geography was not just a backdrop, it was an active player, shaping evolution, dictating who thrived where, and ensuring that the age of dinosaurs was not a single world, but many worlds at once. 66 million years ago, the age of dinosaurs reached its dramatic close. For over 160 million years, they had thrived across every continent, in forests, deserts, swamps, and polar woodlands. Then, in what seems like an instant on the scale of deep time, nearly all of them vanished. The story of the end Cretaceous extinction is not only one of devastation, but also of survival, where catastrophe reshaped the world and opened the way for the age of mammals to begin. The smoking gun of this extinction lies buried in the rocks, a thin layer of clay rich in iridium. Iridium is rare in Earth's crust, but more common in asteroids. This global signature, first recognized in the 1980s, pointed scientists toward the idea of an extraterrestrial impact. Further evidence came in the form of shocked quartz, minerals whose structures were altered by enormous pressure, and tiny glassy droplets called tektites, formed when molten rock was hurled skyward and cooled as it fell. All of these clues converged on a single catastrophic event, the impact of a massive asteroid with Earth. That impact site is now known as the Chicxulub crater, buried beneath the Yucatan Peninsula in Mexico. Over 180 kilometers wide, it marks the scar of an object at least 10 kilometers across, striking Earth at extraordinary speed. The energy released was greater than billions of nuclear bombs, enough to vaporize rock, send towering tsunamis racing across oceans, and hurl dust and debris high into the atmosphere. Forests burned in global wildfires, skies darkened, and the climate reeled from the sudden blow. But the impact was not the only factor. Around the same time, the Deccan Traps in India were erupting with colossal outpourings of lava. These volcanic floods released immense amounts of gases into the atmosphere, including carbon dioxide and sulfur dioxide, altering climate patterns over hundreds of thousands of years. While the asteroid was the decisive strike, the stage may already have been set by a world under stress. The coincidence of volcanism and impact created a 1-2 punch of environmental upheaval that few ecosystems could endure. The immediate effects of the Chicxulub impact were apocalyptic. A rain of molten rock set fires that scorched landscapes. Within hours, the Earth's surface was transformed. Then came the longer crisis. Dust and aerosols thrown high into the atmosphere blocked sunlight for months, perhaps years. Photosynthesis faltered, plant life withered, and food chains collapsed from the bottom up. Herbivores starved, carnivores lost their prey, and the once thriving ecosystems unraveled. Not all life perished, but survival often came down to size, diet, and adaptability. Large non-avian dinosaurs, dependent on vast amounts of food, could not withstand the sudden scarcity. Birds, however, survived. As small feathered theropods, they had the advantage of flight, smaller bodies, and diverse diets. Seeds, insects, and coastal resources provided sustenance through the dark interval. Crocodilians endured too, able to survive long periods without food and to retreat into aquatic refuges where conditions were more stable. Small mammals, with their flexible diets and burrowing habits, also found ways to outlast the catastrophe. The extinction was selective but sweeping. Ammonites vanished, along with most marine reptiles. Pterosaurs, those masters of the skies, disappeared entirely, but turtles, frogs, and fish persisted. Forests eventually recovered, seeds germinating from the soil once the skies cleared. Within a few 100,000 years, geologically a blink of an eye, ecosystems were reborn, though they were no longer dominated by dinosaurs. Instead, mammals expanded into niches left vacant, beginning the rise that would one day lead to primates and much later to us. The loss of the great dinosaurs was not a slow decline but a sudden nightfall. For millions of years they had weathered changes in climate, shifting continents, and volcanic upheavals. They had survived droughts and monsoons, floods and deserts. But the combination of asteroid impact and environmental stress proved too much, too fast. The world they had ruled was plunged into shadow, and they did not emerge from it. And yet their story did not end entirely. Birds, the living descendants of small theropods, carry the dinosaurian legacy forward. When you hear a sparrow outside your window or watch a hawk soar overhead, you are seeing the lineage that survived extinction night. In their feathers, their calls, and their flight, there remains a living connection to a world that once trembled beneath the footsteps of giants. Imagine then the quiet after the storm. The fires have burned low, the skies are still heavy with dust, and silence hangs over once vibrant lands. Then, in time, the air clears, the sun returns, seeds sprout, green shoots break the soil, and small survivors creep out of burrows and nests. Life, patient and resilient, begins again. The great age of dinosaurs may have ended in darkness, but the dawn that followed carried the promise of renewal, a reminder that even after the deepest night, life always finds a way to rise once more. When the great non-avian dinosaurs disappeared at the end of the Cretaceous, it was not the end of their story. Their lineage still moves among us, perched on rooftops, singing from trees and darting across open skies. Birds are dinosaurs, slimmed, feathered, and adapted for a new world, but carrying with them anatomical and behavioural legacies that stretch back to the Mesozoic. Every flap of a wing, every trill of a song, is a continuation of the age that once filled Earth with giants. The path from grounded theropods to airborne birds was not a sudden leap, but a gradual unfolding. Feathers, for example, did not appear first for flight. Early feather-like structures, found in small theropods, were simple filaments, soft, hair-like coverings that may have provided insulation or played roles in display. Over time, these filaments became more complex, branching into structures that could trap air, retain heat, and shimmer with colour. Some were used to impress rivals, some to attract mates, and some to blend into the environment. Only later were feathers co-opted for gliding, and eventually powered flight. The stepwise evolution of wings followed a similar path. Arms that were once tools for grasping prey grew longer, the bones lighter and more flexible. Muscles shifted, joints rotated, and the overall structure transformed into something capable of generating lift. Fossils of transitional species like Archaeopteryx reveal a blend of traits: teeth in the jaws, clawed fingers on the wings, and long bony tails, alongside fully formed flight feathers. These were not yet modern birds, but they show how nature experimented, each adaptation layering onto the last until wings became efficient tools for soaring through the air. Other features of birds trace directly back to their dinosaurian ancestors. Air sacs, which make bird respiration so efficient today, were already present in non-avian theropods. These sacs connected to hollow bones, reducing weight and creating a unidirectional flow of air that kept oxygen moving through the lungs even during exhalation. This system powered high activity levels and supported warm-blooded metabolisms long before the first bird lifted from the ground. Beaks too emerged as jaws lost their teeth in many lineages, trading weight and complexity for lightweight efficiency. Each change was a repurposing of structures shaped not by foresight, but by the pressures of survival and opportunity. Flight itself opened vast new ecological spaces. With wings, dinosaurs could escape predators, reach new food sources, and travel across landscapes in ways no terrestrial animal could match. Trees became both shelter and feeding grounds. Cliffs turned into safe nesting places, and rivers and lakes became accessible hunting grounds from above. Once established, flight drove a burst of diversity. Birds radiated into countless forms: soaring seabirds, forest dwellers, ground runners, and later songbirds whose calls filled entire habitats with sound. The survival of birds through the end Cretaceous extinction underscores the flexibility of this lineage. Small body size, varied diets, and the ability to fly likely helped them endure when larger dinosaurs perished. Seeds may have provided an especially critical food source during the years of darkness that followed the Chicxulub impact. As ecosystems recovered, birds spread rapidly into the gaps left by fallen lineages, their adaptability carrying them across continents and into every environment. Modern bird diversity is staggering. From hummingbirds that weigh less than a coin to albatrosses that glide across oceans with wingspans over 3 meters, the range of forms and behaviors reflects an evolutionary success story unmatched by any other group of vertebrates. The intricate songs of passerines, the courtship dances of cranes, the hunting dives of falcons, all are echoes of Mesozoic experiments refined through time. To see a penguin sliding across ice, or a parrot cracking seeds with its beak, is to glimpse ancient survival strategies recast in new shapes. Birds also carry with them behaviors that feel deeply familiar when viewed in light of their ancestry. Brooding eggs beneath feathers, guarding nests, and teaching young mirror behaviors already seen in non-avian dinosaurs like oviraptorids. Courtship displays with feathers spread and bodies posed recall the crests and frills of ancient relatives. Even the simple act of preening, as a bird smooths and cleans its feathers, has roots in the maintenance of integument that stretches back long before the modern world. To understand birds as living dinosaurs is to change how we perceive the present. The robin on the garden fence, the gull over the waves, and the owl calling in the night are not distant cousins but direct descendants. They are the lineage that endured when fire and darkness swept the world, carrying forward traits honed over tens of millions of years. When we listen to their voices, we're hearing not just modern birdsong but the faint continuation of Mesozoic sounds, reshaped but unbroken. The next time you hear the song of a robin, imagine it as more than a pleasant note in the morning air. Imagine it's a whisper from the past, a reminder that dinosaurs are still here, living among us in feathered form. Their age did not end completely 66 million years ago. It simply transformed. The giants may be gone, but their descendants have filled the skies with colour, sound, and motion. The story of birds is a story of endurance and reinvention. Feathers that once warmed small bodies became wings that carried entire lineages across the globe. Bones that once bore the weight of predators became hollow structures designed for air. Jaws that once bristled with teeth became light beaks specialized for seeds, nectar, or prey. From these transformations arose the nearly 10,000 species of birds alive today, each carrying the unmistakable signature of its ancient heritage. So, when you step outside and hear the flutter of wings or the trill of a songbird, pause for a moment. You're not just listening to the sounds of the present. You're listening to the continuation of the Mesozoic, a chapter that never truly ended. The dinosaurs are still with us, and they are singing. Long before the word dinosaur was ever spoken, people were stumbling across their bones, gigantic femurs eroding from cliffs, teeth the size of knives weathered out of riverbanks, and strange stone eggs tucked in hillsides all found their way into human hands. Without the framework of modern science, these discoveries were folded into myth and legend. A massive femur might be said to belong to a hero of old, a griffin, or even a dragon that once terrorized the land. In China, fossilized bones were sometimes ground into powders called dragon bones and used in traditional medicine. The ancient Greeks thought they were finding relics of titans, while in medieval Europe, such remains were proof of biblical giants. These interpretations were not wrong so much as they were creative attempts to make sense of the deep past without the benefit of geology or paleontology. It wasn't until the 17th and 18th centuries that naturalists began to see fossils as more than curiosities. Some early scholars suggested that the thunderstones and giant bones being found across Europe were actually the remains of ancient animals long dead. This idea was radical at the time, for it implied that Earth's history was far older and stranger than the human imagination had allowed. By the early 1800s, a new science was being born, paleontology. It was a discipline shaped by curiosity, rivalry, and an insatiable appetite for discovery. The first creatures to be recognized as something entirely different from living animals were given names that still capture the imagination. Megalosaurus, described in the 1820s, was one of the earliest. Soon after came Iguanodon, identified from teeth that resembled those of an iguana, but on an impossible scale. These early finds stirred public excitement, leading to sculptures, illustrations, and even life-sized reconstructions in Victorian parks. Although clumsy by modern standards, some reconstructions had Iguanodon sporting a horn on its nose instead of a thumb spike. They captured the thrill of realizing that the Earth was once ruled by creatures unlike anything alive today. Then came the Bone Wars of the late 19th century, one of the most dramatic episodes in scientific history. Two rival paleontologists, Othniel Charles Marsh and Edward Drinker Cope, engaged in a bitter competition to outdo one another in discovering and naming new species. Their expeditions across the American West unearthed vast numbers of fossils, including many of the dinosaurs we know today: Stegosaurus, Triceratops, Diplodocus, and Allosaurus among them. Their feud was fierce, sometimes petty, and occasionally destructive, but it also left behind a treasure trove of specimens that filled museums and cemented dinosaurs as cultural icons. As the 19th century rolled into the 20th, fossil hunting expanded across the globe. Expeditions travelled to Mongolia's Gobi Desert, Argentina's Patagonia, Africa's Rift Valley, and beyond. Each region revealed unique treasures, from the clawed velociraptors of Asia to the towering titanosaurs of South America. These expeditions often blended science with adventure, as paleontologists braved deserts, jungles, and high mountains in search of ancient bones. At times, fossils were taken with little regard for local communities, sparking ethical questions that still resonate today about ownership, cultural heritage, and the responsibilities of science. Museums became the grand stages on which these discoveries were displayed. Vast halls filled with towering skeletons turned stone bones into monuments of memory. To stand beneath a mounted Diplodocus or gaze up at the skull of Tyrannosaurus rex is to feel both small and connected to something immense. These institutions were not just collections of bones, They became palaces of stone, places where deep time was condensed into awe-inspiring forms. For children especially, these skeletons lit sparks of imagination that might grow into lifelong fascinations or even future careers in science. Behind the glass cases and dramatic mounts, the work of paleontology continued to evolve. The 20th century brought new techniques: radiometric dating to determine the ages of rocks, CT scans to peer inside fossilized skulls, and isotopic analysis to reconstruct diets and climates. Today, paleontology is as much about microscopes and computer models as it is about picks and shovels. A single fossil can be studied for decades, yielding insights into growth, metabolism, biomechanics, and even colour patterns. The history of fossil discovery is not only about grand breakthroughs, but also about patience. A fossil must first survive the immense pressures of burial and lithification, then wait millions of years before erosion reveals it once more. It must then be noticed by human eyes, carefully excavated, prepared with painstaking care, and studied across generations. Every fossil that rests in a drawer or on display in a museum has passed through this gauntlet of chance and persistence. Each one is a story carried across deep time to arrive in the present. There is also an undeniable romance in the act of fossil hunting itself. Imagine crouching in a desert, brushing sand from a ridge of bone that has not seen the light of day for 70 million years. The excitement of that moment, of being the first human to touch it, is timeless. Yet, for all the glamour, most of paleontology is slow, careful work. Preparing a single fossil may take years, removing stone grain by grain until the bone is revealed. As much as discoveries fire the imagination, they demand patience, precision, and discipline. Fossils also remind us that science is not fixed but constantly revised. Early reconstructions of dinosaurs portrayed them as lumbering, tail-dragging reptiles. Today, with new evidence, we see them as dynamic, active animals, some feathered, some colourful, and all far more complex than once thought. Our picture of the past is never final. Each fossil discovered adds another brushstroke, refining and sometimes overturning what we thought we knew. From myths of dragons to modern CT scans, fossils have guided humanity's journey into deep time. They are more than stones, they are messages. They tell us that the world has been many worlds, each populated by creatures extraordinary and strange. They remind us of extinction and survival, of the fragility of life and its resilience. And while fossil collecting should always be done with care and respect, please don't chisel the coffee table in search of your very own museum piece. The allure is understandable. To hold a fossil is to cradle a fragment of Earth's memory. To see one in a museum is to stand before a silent storyteller, its voice carried through stone across millions of years. In the end, digging up fossils is digging up dreams. They are dreams set in stone, waiting patiently for us to notice, to study, and to wonder. Through them, we connect not only with the dinosaurs but with the entire history of life on Earth. For most people, the dinosaurs they know best are not the ones described in technical papers, but the ones they have seen in paintings, movies, and animations. The field of paleoart, the artistic reconstruction of ancient life, has played a central role in shaping our collective imagination. From Victorian sculptures of lumbering reptiles to today's feathered, agile predators, the way dinosaurs are drawn and animated has profoundly influenced how we think about them, how we dream about them, and even how science itself is interpreted. To rebuild the past visually is both a gift and a responsibility, balancing evidence with imagination. The earliest public depictions of dinosaurs often reflected the limits of knowledge at the time. In the mid-1800s, when only a handful of skeletons were known, artists created bulky, squat creatures that drag their tails along the ground. The Crystal Palace sculptures in London, unveiled in the 1850s, were marvels of public science, but look comical today, more like giant iguanas or toads than the dynamic animals they truly were. Yet those sculptures stirred wonder, and for many Victorians they were the first glimpse of a vanished world. As discoveries accumulated, depictions changed. The 20th century brought a shift from sluggish reptiles to more active, upright creatures. Paleontologists began to realize that dinosaurs were not evolutionary dead ends, but successful animals with sophisticated adaptations. Artists like Charles R. Knight painted dinosaurs with vigor, postures raised, eyes sharp, bodies alive with tension and motion. These artworks, displayed in major museums, became iconic, fixing new images in the public imagination. Then came the revolution of the late 20th century, when evidence mounted that many theropods had feathers and that dinosaurs were warm-blooded, fast and dynamic. Paleo artists embraced these discoveries, giving us visions of raptors cloaked in plumage, tyrannosaurs roaring in vibrant ecosystems, and sauropods moving with grace rather than sluggishness. The tail draggers of old disappeared, replaced by sleek animals balanced in lifelike poses. Today, paleo art reflects the cutting edge of science, showing dinosaurs as complex, colourful and often bird-like. Yet even the best reconstructions must wrestle with uncertainty. Fossils preserve bones, sometimes skin impressions, and occasionally feathers or pigments, but much of the living animal is left to inference. What exact colours did they wear? How did they move in subtle ways? How did they sound? Paleo artists step into these gaps, guided by evidence but filling spaces with educated speculation. Responsible paleo art signals these uncertainties, sometimes offering multiple interpretations rather than a single definitive image. After all, a painting can be so persuasive that it fixes an idea as truth in the mind of the viewer, even if it is only one possibility among many. This is where caution becomes essential. Every piece of paleo art is not just an illustration, but a teacher. It shapes how children first imagine dinosaurs, how adults remember them, and how culture at large frames them. When artists chose to depict dinosaurs as swamp-dwelling brutes, generations believed that image. When they later showed them as swift, feathered hunters, public understanding shifted again. Visuals have the power to solidify knowledge or to mislead. The responsibility of paleo art is therefore not just to entertain but to illuminate, reminding viewers where evidence ends and imagination begins. Animation has added another layer to this story. From early stop-motion films to the computer-generated marvels of modern cinema, dinosaurs on screen have brought prehistory to life in ways no static painting could. Movies like the original Jurassic Park cemented images of velociraptors that were sleek, scaly, and terrifying, even though the real animals were feathered and smaller. The spectacle was unforgettable, but it also fixed inaccuracies in the public mind. Such moments show both the power and the pitfalls of visual storytelling. People rarely forget what they see, even when science later moves on. At the same time, animations and documentaries have provided opportunities for nuance. Scientific collaborations with artists and filmmakers have produced reconstructions more faithful to evidence than ever before. High-definition animations now portray feathered raptors preening, sauropods moving in herds, and hadrosaurs calling across wetlands. These visualizations invite us not only to learn, but to feel connected to the long-lost world, sparking both curiosity and empathy for creatures long gone. For those watching late at night, these images can drift into the realm of dreams. A sketch of a dinosaur under a lamp, an animation of wings beating against ancient skies, or a painting of herds beneath strange constellations. All can settle into the imagination, weaving prehistoric life into bedtime thoughts. paleoart is not only about scientific accuracy, but also about emotional resonance, the ability to make the distant past vivid enough to enter our stories and even our sleep. The role of the paleoartist is therefore unique. They stand at the intersection of science and imagination, tasked with building bridges between bones and beings, between data and dreams. Their work requires fidelity to evidence, humility in the face of uncertainty, and creativity to bring the silent stones to life. With a single stroke of colour or adjustment of posture, they can either reinforce accuracy or create myths that linger for decades. And yet, there is joy in this process. To sit at a desk, a lamp casting warm light over paper or a digital screen, and to sketch a creature that has not walked the earth for tens of millions of years, is to participate in a kind of time travel. The artist leans on science, but also on empathy, asking, how would it feel to move in this body, to breathe through these lungs, to live in this world? In that quiet act of drawing or animating, the Mesozoic becomes a little less distant. Over time, paleoart has evolved alongside paleontology itself. Each discovery reshapes the images, and each image, in turn, influences how discoveries are received by the wider world. The process is cyclical. Fossils inform art, art informs culture, and culture inspires new curiosity that leads back to fossils. This interplay has ensured that dinosaurs remain not only scientific subjects, but cultural icons, forever alive in our imaginations. So when you see a painting of a feathered dromaeosaur or an animation of a sauropod herd, remember that you're looking at more than just art. You're looking at a conversation across time, between stone and imagination, between science and creativity. It is a delicate balance, one that requires honesty, responsibility, and wonder. Because every sketch, every sculpture, every animated frame has the power to bring the deep past into the present, and perhaps even into the dreams of those who fall asleep with dinosaurs on their mind. For all that has been uncovered about dinosaurs, the greatest source of fascination lies in what remains hidden. Fossils give us bones, footprints, eggs, and occasionally impressions of skin or feathers, but so much of life is lived in the moments that do not fossilize. The day-to-day behaviours, the sounds, the colours, the interactions. All these subtleties often slip beyond our reach. This uncertainty is not a weakness of paleontology, but one of its strengths, for it leaves space for wonder, and it keeps the story of dinosaurs forever open to discovery. Take, for instance, the question of vocalizations. Did a hadrosaur's hollow crest resonate with deep, foghorn-like calls that carried for kilometres across wetlands? Did a tyrannosaur growl, hiss, or produce low rumbles more akin to a crocodile's bellow? Some evidence, like the resonating structures in crested hadrosaurs, hints at communication, but the precise soundscapes of the Mesozoic remain speculative. Even with modern technology, sound does not fossilize, and so the roars and songs of dinosaurs remain one of nature's most tantalizing mysteries. Social structures present another great puzzle. Fossilized bone beds containing dozens of individuals suggest that some species lived in groups, perhaps herds or colonies. But how those groups were organized, whether they were dominated by a single leader, arranged in family units, or more loosely gathered, cannot be read directly from stone. Did tyrannosaurs hunt in packs, coordinating like wolves, or were they opportunistic loners, tolerating each other only at carcasses? Did sauropods move in protective circles around their young, as elephants do today, or simply follow one another across landscapes without complex coordination? These questions remain partly unanswerable, yet they stir the imagination and remind us how much more there is to learn. Seasonal migrations are another area of uncertainty. In polar regions where dinosaurs lived through months of light and darkness, did they stay year-round, adapting to the conditions, or did they migrate vast distances in search of milder climates? Trackways suggest movement, but the full scale of migrations, whether thousands of kilometres or more modest journeys, remains difficult to pin down. The very idea of herds of hadrosaurs trudging beneath auroras or flocks of early birds crossing seas is both plausible and poetic, a story still waiting for evidence to fill its outlines. Lifespan is another mystery. Growth rings in bones provide some clues, showing bursts of growth in youth and slower rates in maturity, much like trees. From these, paleontologists estimate lifespans, a few decades for many large dinosaurs, perhaps longer for some sauropods. But was there an upper limit, a natural old age that few reached? Did disease or injury cut lives short more often than time itself? Fossils occasionally show signs of tumours, arthritis, or healed wounds, revealing that dinosaurs suffered from ailments much like modern animals. Yet the broader patterns of health, disease, and longevity remain hazy. Even behaviours as simple as sleep are elusive. Did dinosaurs rest in flocks like modern birds taking turns to keep watch? Did predators nap under shade at midday, or did they prowl through the night? A few fossils show individuals curled up in sleep-like poses, feathers tucked neatly, but whether this was common across species or an exception is still unclear. The rhythms of their days, their circadian cycles, their habits of rest and activity remain largely hidden from us. The exciting part is that new techniques promise to bring us closer to these answers. Advances in imaging, such as high-resolution CT scans, allow researchers to peer inside fossilized skulls, reconstructing brain cavities and inner ears to estimate sensory capabilities. Geochemical analyses reveal traces of proteins and pigments that hint at original colors or diets. Synchrotron radiation, a powerful form of X-ray, can uncover microscopic structures invisible to the naked eye. Even ancient DNA, though degraded beyond use for dinosaurs, inspires techniques for analyzing molecules that may survive for tens of millions of years. Each innovation opens a new window into lives long gone. The future of paleontology also lies in collaboration. Robotics engineers test how tails might have balanced bodies in motion. Computer modelers simulate herds moving across landscapes. Ecologists study modern animals as analogues for extinct ones, drawing parallels that might shed light on dinosaur behaviour. Every discipline adds new layers, reminding us that the puzzle of prehistory is not solved in isolation, but through shared curiosity. And there are always new discoveries waiting in the ground. A single fossil find can overturn long-held assumptions. A feathered dinosaur in China reshaped our image of theropods. A nesting site in Mongolia revealed brooding behaviour. An exquisitely preserved nodosaur in Canada showed stomach contents and skin texture. Somewhere, beneath a hillside or desert dune, another fossil rests, waiting to expand the boundaries of what we know. What we do not know is vast, but it is not empty. It is fertile ground for questions. Did some dinosaurs care for their elderly, or abandon them? Did they recognize individuals in their herds by sight, sound, or smell? Were some species nocturnal, their eyes adapted for moonlit hunting? Did young dinosaurs play, chasing and sparring as practice for adulthood? Each possibility is a story half told, a reminder that science is a dialogue with the unknown. What makes this uncertainty so compelling is that it does not diminish dinosaurs but makes them more vivid. To imagine a world full of animals whose sounds, colours and behaviours we can only partly guess is to embrace the wonder of science itself. Knowledge grows, but mystery endures, giving us reason to keep asking, searching and dreaming. The sand, in its quiet way, remembers every step. Fossilized footprints are proof of this, fleeting moments of life captured in stone, from herds moving across plains to a single animal pausing to rest. These traces remind us that even if we never know every detail, the earth holds the memory of their presence. Each unanswered question is an invitation to look closer, to dig deeper, and to keep the dream of discovery alive. The story of dinosaurs is a story told across unimaginable spans of time, yet it has accompanied us here to this quiet moment. From the earliest small and nimble creatures darting across the dry Triassic plains, to the vast sauropods that shook the ground with every step, to the horned and frilled giants of the Cretaceous, their history unfolds like a symphony of life, beginning in faint notes, swelling into thunder, and finally tapering into the delicate songs of birds in the morning light. To think of them is to think of resilience, of how life can endure catastrophe after catastrophe, adapting and reshaping itself again and again. After the world's greatest extinction at the end of the Permian, it was small, fragile forms that emerged into the dawn of the dinosaurs. After the Chicxulub impact ended their reign, it was their feathered descendants that lifted themselves into the skies and survived. Each chapter of their history reminds us that survival is not always about being the biggest or strongest, but about flexibility, persistence, and sometimes just being in the right place at the right time. Science, in its quiet way, lets us listen to these ancient lives. A fossil bone does not speak, yet it holds whispers in its structure, growth rings that reveal how fast an animal grew, scars that hint at injuries survived, hollow spaces that once held air sacs breathing life into colossal bodies. Sediment remembers the shape of nests, the rhythm of floodplains, the passage of herds. Even the chemistry of ancient shells can recall the warmth of Cretaceous seas. To study these things is to practice patience, to lean close to the stones of the earth and learn to hear what they remember. We cannot know everything. Dinosaurs lived in vibrant worlds full of colours, sounds and movements that are forever lost to us. Yet what we do know is enough to feel their presence. We can picture a herd of hadrosaurs moving through wetlands, their calls rolling like distant thunder. We can imagine a lone ceratopsian silhouetted beneath the moon, frill aglow in the pale light. We can see a small dromaeosaur preening its feathers as dusk settles. These are reconstructions, shaped by science but coloured by imagination, and they remind us that the boundary between knowledge and wonder is where fascination thrives. It is humbling to reflect on how brief our own story is by comparison. Humans have walked the earth for only a fraction of the time dinosaurs ruled it, yet we can hold their bones, study their footprints, and trace the arc of their lives across millions of years. In doing so, we place ourselves within a much larger tapestry, one woven by countless generations of creatures who came before us. Their presence reminds us that life is never still, that everything we know today is part of a continuum stretching far behind and far ahead. There is also gratitude to be felt, gratitude that stone and time preserve these traces for us, gratitude that we live in an age where science allows us to read them, gratitude that even though the great herds are gone, their songs have not ended but simply transformed into the calls of birds at dawn. When we listen to a robin, a blackbird, or a sparrow, we are hearing the survivors of an age of giants. The dinosaurs did not truly vanish. They simply changed their form and continued, woven into the living world that surrounds us now. To let these thoughts accompany you into rest is to find a kind of calm. Dinosaurs remind us of impermanence, but also of continuity. They remind us that endings are also beginnings, that loss is often paired with renewal. Their bones, their feathers, their footprints are not just relics, but gentle teachers, guiding us toward patience, resilience, and curiosity. So tonight, as you drift towards sleep, let the images of deep time settle around you like a soft quilt. Imagine ferns swaying in warm breezes, the low rumble of distant footsteps fading into silence, and above all, the quiet flutter of wings as dawn breaks over a world both ancient and familiar. May your dreams wander safely among the ferns, accompanied by the gentle company of creatures who once ruled the earth, and who, in their own way, still do.